In approximately 5 billion years, the Sun will exhaust its primary fuel source, the hydrogen in its core. The delicate balance between the outward pressure of nuclear fusion and the inward crush of gravity will begin to tilt. The core will contract, heating up, and this heat will push the outer layers of the Sun outward, swelling it into a red giant. This bloated star will expand to encompass the orbits of Mercury and Venus, and its outer edge will likely reach Earth. The oceans will boil away. The atmosphere will be stripped. The surface will become a molten, sterile wasteland. This is the end of Earth as a living world. But this is not the end of the cosmos. It is merely a single local death in an ocean of cosmic time. The universe, it seems, has a much larger, much stranger, and far more terrifying story to tell about its own end. A story that might not be an end at all, but a beginning, a cycle of death and rebirth so vast and so complete that it challenges our very understanding of time itself. We look at the universe as it is today, a vast web of galaxies, each containing billions of stars, and we imagine it is eternal. But the laws of physics, the same laws that dictate the life and death of a star, also dictate the life and death of the entire cosmos. There are three primary paths to the end of everything, and each is dictated by a single mysterious property of the universe, its expansion rate. For a century, we have known that the universe is expanding. Galaxies are flying away from us. But for a long time, we did not know if this expansion would slow down, stop, and reverse, or if it would continue forever. The answer, which we have only recently begun to understand, determines the fate of all things. The first possibility, the one that was the most intuitive for early cosmologists, is the Big Crunch. Imagine throwing a ball into the air. It rises, slows, stops, and then falls back to Earth. Gravity is the force that pulls it back. In the same way, the gravity of all the matter in the universe should be pulling on the fabric of space itself, trying to slow the expansion. If the universe had enough mass, the expansion would eventually halt. Then, the ball would fall back. The expansion would reverse. Galaxies that were flying apart would begin to drift towards each other. At first, this would be a slow, almost imperceptible process, but over billions of years, it would accelerate. The cosmic recession would become a cosmic infall. The universe would begin to contract. This is the Big Crunch. For many people, the Big Crunch sounds like a final apocalyptic destruction, and it is. But let's reframe that. It is more accurate to think of it as a reunion. All the matter and energy that has been spread out by the expansion, that has been separated into lonely clusters of stars and islands of galaxies, is being pulled back together. It is a return to the source. As the contraction accelerates, the universe gets smaller and hotter. The empty voids between galaxies collapse. The galaxies themselves begin to merge. Stars that were once billions of light years apart are now crowded into a searing, chaotic maelstrom. The night sky, which was once a dark canvas dotted with distant lights, becomes a solid, white-hot furnace in every direction. The temperature rises to millions, then billions of degrees. Stars are ripped apart. Planets are vaporized. Atoms themselves are torn into their constituent particles. Finally, all of the matter and energy in the universe is compressed into an impossibly dense, infinitely hot point, a singularity. This is the same state that we believe existed at the moment of the Big Bang. The Big Crunch is not just an end. It is the mirror image of the beginning. It is a reunion of all that was ever separated. For a long time, this was a leading theory. It was elegant, it was symmetrical, The universe had a beginning and an end, a breath in and a breath out. But then, we discovered something that shattered this beautiful symmetry. We discovered that the expansion of the universe is not slowing down, it is speeding up. We call the force driving this acceleration dark energy. Think of it as a kind of anti-gravity. Normal gravity pulls things together. Dark energy pushes things apart. It is a property of empty space itself. As the universe expands, more empty space is created, and this new space has its own repulsive energy, speeding up the expansion even further. This acceleration is the key to everything. The discovery of dark energy has profound implications for the fate of the cosmos, because if the universe is accelerating, then the big crunch is off the table. The expansion is not going to stop. It is not going to reverse. It is going to go faster and faster forever. This leads us to the second, far more likely, and frankly, far more chilling end. The Big Freeze, also known as the heat death of the universe. This is the scenario we are currently on track for. To understand the Big Freeze, we have to understand a concept called entropy. Entropy is often described as a measure of disorder, but a more accurate definition is a measure of energy distribution. A system with low entropy has energy concentrated in a small area, like a hot cup of coffee in a cold room. A system with high entropy has energy spread out evenly, like the coffee and the room reaching the same lukewarm temperature. The universe is a closed system, and entropy always increases. The Big Freeze is the ultimate victory of entropy. Because the universe is accelerating, everything is being pulled apart. Galaxies are moving away from each other so fast that eventually they will be completely isolated. The light from other galaxies will never reach us. The night sky will become completely black. Every star will eventually burn out. Billions upon billions of years from now, the last star will fizzle, leaving only the corpses of stars, white dwarfs, neutron stars, and black holes. But even black holes are not permanent. Stephen Hawking showed us that black holes actually evaporate, slowly leaking energy in the form of Hawking radiation. Over unimaginably long timescales, even the supermassive black holes at the centers of galaxies will dissolve into a faint mist of particles. The universe becomes a cold, dark, empty void. There are no stars, there is no heat, there is no light. There is only a diffuse, ever-thinning soup of fundamental particles and low-energy photons. Everything is the same temperature, just a fraction of a degree above absolute zero. This is the heat death. There is no more energy to do anything. No reactions can happen. No structures can form. Time itself becomes meaningless because nothing can change. This is the most likely end of the universe. A quiet, empty, eternal stillness. It is not a dramatic explosion. It is a long, slow, quiet suffocation. But there is a third, even more bizarre possibility. What if the acceleration continues to increase, becoming so violent that it doesn't just pull galaxies apart? What if it pulls apart the very fabric of space itself? This is the Big Rip. In the Big Crunch, gravity wins. In the Big Freeze, dark energy wins, but it wins slowly. In the Big Rip, dark energy wins instantly. The acceleration becomes infinite. The repulsive force becomes so strong that it overwhelms every other force in the universe. First, it tears apart galaxy clusters, then galaxies, then solar systems, then planets, then stars. Then it starts to tear apart atoms. The electromagnetic force that holds electrons to their nuclei is no match for the screaming expansion of space. Atoms are ripped apart into their constituent quarks and leptons. Finally, the very fabric of space-time itself is torn. Space and time cease to exist as we know them. There is no singularity, no crunch, no final moment. There is just a snapping, a shredding, a dissolution into nothingness. This is the most violent and terrifying end imaginable. And whether we face the big freeze or the big rip depends on the precise nature of dark energy, which we still do not understand. Let's define this term that is crucial to the future: the speed of darkness. You have heard of the speed of light, the cosmic speed limit. The speed of darkness is not a speed that anything travels at. It is a speed of creation. It refers to the rate at which new space is being created between distant galaxies, driven by dark energy. Imagine 2 points in space. The light from one point travels to the other at 300,000 kilometers per second. But if the space between them is expanding, that light has to travel through an ever-growing distance. The speed of darkness is the rate at which that distance is increasing. If the expansion rate is high enough, the distance between two objects can grow faster than the speed of light. This is allowed because it is space itself that is stretching, not an object moving through space. When this happens, the light from those distant galaxies can never reach us. They are carried away over the cosmic horizon. They are lost forever in the darkness. The speed of darkness is the rate at which the universe is being torn apart and rendered invisible. It is the speed of cosmic isolation. This is a direct connection to dark energy. Dark energy is the engine. The speed of darkness is the measure of its power. The faster the speed of darkness, the faster the universe accelerates, and the sooner the big freeze or big rip will come. Now, let's tie this to the concept of emotional drift. This is a human metaphor for a cosmic process. Entropy is often described as cold and sterile, but think about it. The increasing entropy of the universe, the spreading out of energy, is mirrored in the increasing distance between everything. As the universe expands and cools, interactions become less frequent. The probability of anything interesting happening decreases. This is a form of cosmic loneliness, the heat. Death is the ultimate state of emotional drift. There is no other to interact with. There is no energy to feel. There is no change to experience. It is a state of perfect eternal isolation. Dark energy is the cause of this drift. It is the force that is making the universe less connected, less dynamic, and ultimately less alive. It is the force of cosmic separation, pulling the tapestry of reality apart thread by thread. But here is the hope. The strange, cyclical hope. The big crunch might be impossible in our current universe, but what about a universe that doesn't have a beginning? What about a universe that has no end because it is eternal? This brings us to the big bounce. This theory is not just a wish. It is a serious mathematical concept born from a theory called loop quantum gravity. The problem with the big crunch is that it leads to a singularity, a point of infinite density where physics breaks down. We know singularities are a sign that our equations are incomplete. Loop quantum gravity suggests that space-time is not a smooth fabric. It is made of tiny, discrete quanta, like pixels on a screen. It is granular. When you compress matter to an extreme density, you do not get an infinite point. You get a quantum bounce. The repulsive forces of this granular space-time kick in, preventing the collapse into infinity. The universe contracts until it reaches a maximum density. and then it bounces back out in a new Big Bang. This changes everything. In the Big Bounce model, there is no beginning. There is no end. Our universe is just one in an endless chain of universes. It expands, it contracts, it bounces, and expands again. Each cycle can last for trillions of years. The matter and energy of our universe is not destroyed in the crunch. It is recycled. The information of the previous universe, perhaps even the patterns of its galaxies and structures, might be imprinted on the quantum fluctuations of the next universe. The universe is a phoenix. It dies in a fiery crunch and is reborn in a brilliant bang. The evidence for this is not conclusive, but it is compelling. The Big Bounce solves the singularity problem, which is a huge mark in its favor. It also provides a natural explanation for the flatness and homogeneity of our universe, properties that are otherwise very difficult to explain without invoking a period of rapid inflation at the very beginning. If the universe has been bouncing for eternity, it has had infinite time to smooth out any irregularities. It also addresses the arrow of time. Why does time move forward? In an oscillating universe, time has no ultimate direction. It is a cycle. The beginning of our Big Bang is simply the end of the previous big crunch. The end of our big freeze is simply the beginning of a new contraction. The idea of a no beginning, no end claim is not just philosophical. It is a direct mathematical consequence of loop quantum gravity. The equations show that the universe can be described as a closed system that cycles forever. There is no moment of creation because there is no point where the equations break down. The universe has always existed in some form, and it will always exist. This is a radical shift from the standard Big Bang model. It removes the need for a first cause. It makes the cosmos truly eternal. Think about what this means for the end of the Earth. The Earth will be destroyed by the Sun. That is a certainty. But the universe itself? The universe will either die in a cold, lonely heat death, or it will be torn apart in a violent big rip. Or it might bounce back. It might collapse back into a tiny hyperdense seed, only to explode again. In this infinite cycle, our Earth, our Sun, our galaxy, all of our history is just a single heartbeat in an eternal pulse. The matter that makes up your body has been through this cycle an infinite number of times. It has been part of stars that exploded in the previous universe. It has been crushed into the singularity of a previous big crunch. It has been scattered as primordial gas in the next. We are made of the ashes of dead universes. The death of the Earth is not the end. It is a transition. The heat death of the universe is not the end, it is a rest. The big crunch is not a destruction, it is a reunion. The Big Bounce is not a theory of doom. It is a theory of hope. It is the realization that the cosmos is not a fragile, temporary thing. It is a machine, a clockwork of infinite cycles. Death is not the opposite of life. It is a part of a process. The end of the cosmos is not an edge, it is a door. We stand on a small rock orbiting a dying star in a universe that is accelerating towards its own dissolution. We look up at the stars and we know they will all go out. We look at the galaxies and we know they will all fade, but we also see the pattern. We see the cycle. We see the beginning in the end. We see the death that is necessary for rebirth. The universe is not an accident. It is a story, and the story does not end with the last star. It ends with a new beginning, and then another, and another, forever. This is the infinite death cycle. It is not something to fear. It is something to understand. It is the rhythm of reality. And we, for a brief and brilliant moment, are alive to witness it. But what does it mean to witness such a thing? To be a brief flicker of consciousness in a universe that spans trillions of years and an infinite chain of bounces. It means that we are not simply passengers on a one-way journey toward a cold, dark end. We are active participants in a process that has no beginning and no end. The same energy that fuels the nuclear furnace of the sun, the same quantum fluctuations that seeded the galaxies, the same dark energy that is now pulling the universe apart. All of it is part of a single self-sustaining loop. And within that loop, life emerges, evolves, and eventually fades, only to be recycled into the next cycle of creation. The Big Bounce theory has been refined over the past 2 decades, and it does not rely solely on philosophical preference. It is grounded in the mathematics of loop quantum gravity, which treats space-time as a network of discrete loops. When the universe contracts to a very small size, these loops interact in a way that generates a repulsive force. The density never reaches infinity. Instead, the contraction halts and reverses. This is not a hypothetical hand-wavy idea. Computer simulations of loop quantum cosmology show that a universe with our observed properties, flatness, homogeneity, the slight fluctuations that became galaxies, can emerge naturally from a previous contracting phase. The so-called no-boundary proposal, where time has no beginning, is also supported by these models. But perhaps the most compelling evidence comes from a surprising place: the cosmic microwave background. The CMB is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. It is almost perfectly uniform, with tiny temperature variations that match the predictions of inflationary cosmology. However, inflation has its own problems. It requires a very specific set of initial conditions and a mysterious inflation field. The Big Bounce provides an alternative. The universe could have been smoothed out by a long period of contraction before the bounce, eliminating the need for a sudden, fine-tuned inflation. Some researchers have even found that the pattern of CMB fluctuations might show faint signatures of a previous cycle, for example, a suppression of power at large angular scales. These are subtle hints, but they are consistent with what a bouncing universe would produce. Let's go deeper into the relationship between dark energy and entropy. Entropy is often misunderstood as mere disorder, but in the context of the cosmos, it is the measure of how evenly energy is spread. Dark energy, by accelerating the expansion, creates more volume for the same amount of energy. This rapidly increases entropy because it allows the universe to approach thermodynamic equilibrium faster. The emotional drift I mentioned earlier is not just a poetic metaphor. It is the human reflection of this cosmic process. As the universe expands and matter becomes more isolated, the chances for interaction, for complexity, for novelty, all of which we associate with meaning and emotion, diminish. The universe becomes a place of increasing loneliness. Dark energy is the engine of this drift, pushing galaxies apart so that even the light from the nearest neighbor takes billions of years to arrive, until eventually it never arrives at all. This is the cold heart of the heat death, a state where all potential for change is exhausted. The only thing left is the slow, patient decay of black holes. But if the Big Bounce is real, then dark energy is not the final word. The same repulsive force that accelerates the expansion might eventually weaken or change its nature. Some models suggest that dark energy could decay over time, allowing gravity to reassert itself after trillions of years. The universe would then stop expanding, begin to contract, and head toward the Big Crunch. But now we must clarify. The Big Crunch is not a destruction, it is a reunion. Every particle that was ever separated by the expansion will come back together. Every photon that has been traveling for billions of years will be gathered into the singularity. It is a homecoming. It is the universe remembering its original unity. In the Big Bounce, that reunion is not an ending, but a transition. The singularity is avoided. Instead, the universe reaches a maximum density and then bounces outward, carrying the memory of everything that came before. This brings us to the ultimate question. Does the universe have a purpose? If it cycles forever, then every action, every life, every tragedy and triumph is part of an eternal recurrence. The atoms in your body have been part of countless stars, planets, and perhaps even civilizations in past cycles. You are the product of an infinite history. The speed of darkness that is currently tearing our universe apart is also the force that will eventually bring it back together. It is the rhythm of the cosmos, expansion and contraction, death and rebirth, separation and reunion. We are not at the edge of time. We are at the midpoint of a pulse. And what of the Earth? Our planet will be swallowed by the sun in about 5 billion years. That is a local event, a tragedy on a planetary scale, but it is also a necessary step in the larger cycle. The sun, like all stars, is a temporary concentration of energy. It will die, and its matter will be scattered into the interstellar medium. Some of that matter will eventually form new stars, new planets, perhaps new life. Even if humans are long gone, the universe will continue to create. The end of the Earth is not the end of the cosmos. It is a small note in a symphony that never ends. Now, let's examine the concept of the block universe and how it relates to the cycle. In the block universe model, all of time, past, present, future, exists simultaneously as a static four-dimensional block. From that perspective, the Big Bang does not happen before the Big Crunch. They are just different slices of the same eternal object. If the universe bounces, then the block contains an infinite sequence of bounces. Every moment of every cycle is equally real. You, reading this script, exist in the block. The heat-death of the universe exists in the block. The next Big Bang exists in the block. There is no flow of time. There is only the geometry of space-time. This may sound abstract, but it has profound implications for how we view our own mortality. The experience of time passing is an illusion. We are just surfing along a specific world line. But in the block, everything is already there. The cycle is complete. The evidence for the no beginning, no end claim does not only come from loop quantum gravity. There is also the possibility of a cyclic universe based on string theory. In the 1990s, physicists Paul Steinhardt and Neil Turok proposed a model where our universe is a three-dimensional brain floating in a higher dimensional space. Every few trillion years, another brain collides with ours, triggering a Big Bang. In this model, dark energy is not a mysterious force, but the result of the interplay between brains. Each collision resets the universe, erasing some features while preserving others. This model also avoids a singularity and provides a natural explanation for the arrow of time. It is not the only cyclic model, but it shows that the idea has multiple foundations. So where does that leave us? We are faced with three possible futures: the big freeze, the big rip, or the big bounce. Each is supported by different assumptions about dark energy and gravity. The big freeze is the most likely based on current observations, but those observations are limited. We do not know if dark energy is constant or if it changes over time. If it changes, the big rip becomes possible. If it changes in the opposite direction, the big crunch becomes possible again. And if quantum gravity is correct, the big bounce is inevitable no matter what dark energy does. The only way to know for sure is to continue observing the universe, to measure the expansion history with more precision, to detect gravitational waves from the early universe, to search for signatures of a previous cycle in the CMB. But for now, we can choose our narrative. We can see the end as a cold, meaningless drift, or we can see it as a necessary step in an eternal dance. The science is not settled, but the beauty of the cosmos is that it allows for possibility. The death of our sun is a certainty, but the death of the cosmos is not. There may be no final edge to time. There may be only a forever unfolding of cycles, each one a little different, each one carrying the echoes of all that came before. We are the universe becoming aware of itself. We are the part of the cycle that looks back and asks, why? And the answer is not in a book or a formula. The answer is in the pattern itself. The universe does not end, it transforms. The darkness is not an enemy, it is the canvas upon which the next light will be painted. The speed of darkness is the speed of creation. Entropy is not the enemy of life. It is the force that drives the cycle, ensuring that no energy is wasted. The big crunch is not a punishment, it is a hug. The big freeze is not a finality, it is a deep rest between heartbeats. The earth will end, the sun will die, the Milky Way will merge with Andromeda, the stars will all go out, but the universe will go on. It will contract or bounce or dissolve into a mist of particles, but it will go on. And somewhere, in some form, consciousness will arise again. It might be different from ours, it might be unimaginable, but it will be. Because the cycle is infinite, and in an infinite cycle, everything that can happen will happen, an infinite number of times. We are not at the end. We are not at the beginning. We are just here now, witnessing a small sliver of the infinite. That is enough. That is everything. The end of the earth and the cosmos is not a tragedy, it is a chapter. And the book has no final page. The story continues forever. And so, the narrative we carry is not merely a scientific hypothesis. It is a lens through which we view our own existence. The universe's infinite death cycle is not a distant abstraction. It is the ground beneath our feet, the air in our lungs, the fire in our stars. Every moment of cosmic change is mirrored in the human experience: birth, growth, decay, and transformation. The emotional drift we feel, the sense of isolation in an accelerating world, is not a malfunction of our psyche. It is the echo of dark energy, the same force that is pulling galaxies apart, now pulling us into ourselves, fragmenting communities, diluting meaning. But in the cycle, that drift is temporary. The contraction that follows reconnects. The reunion that is the big crunch is the ultimate healing of separation. To understand the speed of darkness, we must first understand that darkness is not an absence of light. It is the limit of light. As the universe expands faster than light can travel across intergalactic voids, the darkness we see is the leading edge of that expansion. The speed of darkness is the rate at which the observable universe loses contact with itself. It is the horizon of our cosmic loneliness, but in the Big Bounce, that horizon is not a wall. It is a threshold. When the universe stops expanding and begins to contract, the speed of darkness reverses. Light that was once fleeing now returns. Galaxies that were isolated converge. The darkness recedes, and the universe becomes visible again, piece by piece, until everything is gathered into the final luminous embrace. The no beginning, no end claim of the Big Bounce finds its strongest footing in the mathematics of loop quantum cosmology. In this framework, the classical singularity is replaced by a quantum bridge. The universe does not explode from nothing. It emerges from a previous collapse. The bounce occurs when the density of the universe reaches a critical value, about 1 billion times the density of an atomic nucleus, and the repulsive force of quantum geometry overwhelms gravity. This repulsive force is a direct prediction of the discrete nature of space-time. It is not added by hand, it falls out of the equations. And once the bounce happens, the new expanding phase carries the seeds of the previous cycle. Long wavelength gravitational waves, a slight asymmetry between matter and antimatter, and the faint residual glow of a past universe. Observations of the cosmic microwave background already show hints of this, a slight suppression of large-scale fluctuations that are difficult to explain with inflation alone. Future experiments, such as the upcoming gravitational wave observatories or improved CMB polarization measurements, could confirm or refute this signature. We live in a time of profound uncertainty. The fate of the cosmos is not yet written, but the beauty of science is that it allows us to hold multiple possibilities in our minds at once. We can prepare for the big freeze while hoping for the big bounce. We can accept the death of the Earth while celebrating the cycle that gave us life. The atomic nuclei in your body were forged in a star that died billions of years ago. The carbon in your DNA was part of a planetary nebula that will seed new worlds. The energy that powers your thoughts is borrowed from the same nuclear fusion that will eventually consume our sun. You are a temporary arrangement of matter that has been rearranging itself for 13.8 billion years and will continue to rearrange itself for trillions more. So, let go of the fear of endings. The end of the Earth is not the end of you. The end of the cosmos is not the end of everything. The cycle is the constant. The rhythm is the truth. And in that truth, we find a strange, profound peace. We are not trapped in a dying universe. We are part of a living, breathing, pulsing cosmos that has no beginning and no end. We are the universe's way of knowing itself, even as it prepares to be reborn. The darkness is not the end, it is the womb. And from that womb, a new light will emerge, carrying the memories of all that came before. The story continues forever. We live on a tiny blue planet, floating through an endless ocean of darkness. And the universe? It is not our friend. It doesn't care about us. It doesn't even know we exist. And that, more than anything, is what makes the situation so terrifying. We walk around every day thinking that tomorrow will be the same as today. The sun will rise, the birds will chirp, your coffee will taste the same. But the truth is, there are countless ways that the entire world could end. Not in 1 billion years, not in 1 million years, tomorrow. Literally tomorrow. And I am not talking about the obvious stuff, not about nuclear war, not about a giant asteroid you can see coming on the news weeks in advance. I am talking about the silent, invisible cosmic horrors that could snuff out every life on this planet in an instant, with no warning, no chance to run, no hope of survival. Some of these events was more likely than you think. And when you really understand the last one, it might just change the way you look at the night sky forever. Let us start with something that wanders the galaxy alone. Something that even Albert Einstein, the greatest mind of the 20th century, initially refused to believe could actually exist. He called it a mathematical curiosity, a bizarre prediction of his own equations that he thought nature would never allow. But nature does not care about what we believe, and these objects are real. They are out there right now, drifting invisibly through the void. They are called rogue black holes, and if one of them ever comes near our little blue planet, it would not even have to touch us to end all life on Earth forever. The worst part is we would never see it coming. When most people think about black holes, they imagine the supermassive monsters at the centers of galaxies, millions or billions of times the mass of our sun, swallowing entire star systems. But those are not the ones we need to worry about. Not for this scenario. The real threat comes from the small ones, the stellar mass black holes. These are born when a massive star, many times heavier than our sun, reaches the end of its life. The star runs out of nuclear fuel. Its core can no longer support the crushing weight of its own gravity, and it collapses inward with unimaginable force. The result is a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. And here is the part that should keep you up at night. That black hole does not stay where it was born. It gets kicked out into the galaxy. It drifts. It wanders, alone, silent, and completely invisible. These black holes are much, much smaller than you might think. Our sun is about 1.4 million kilometers wide. Giant stars like Betelgeuse are over 1 billion kilometers wide, so large that if you put one in the center of our solar system, it would swallow the orbit of Jupiter. But a black hole with the same mass as our sun would be just 6 kilometers wide. That is about the size of a small city. Imagine the entire mass of a star, all that gravity, all that destructive power, compressed into an object you could drive across in 10 minutes. That makes them nearly impossible to detect. We cannot see them directly. We can only infer their presence by how they interact with their environment. Sometimes we catch them sucking matter off a nearby star, creating a bright disk of superheated gas. Sometimes we see a star whipping around an invisible point in space, its orbit betraying the presence of a massive dark companion. And sometimes, very rarely, we detect them through gravitational lensing, where the black hole's gravity bends the light of stars behind it like a cosmic magnifying glass. But here is the problem. We have only found a handful of these rogue black holes, maybe a few dozen at most. And yet, astronomers estimate that there could be as many as 500 million of them wandering our Milky Way galaxy alone. That number is not a guess. It is based on our understanding of how many massive stars have lived and died over the life of the galaxy. 500 million invisible city-sized objects, each one capable of destroying our planet, drifting through the space around us. If they are evenly distributed throughout the galaxy, which is a reasonable assumption, then there should be a rogue black hole within about 50 light-years of Earth right now. That is close. Cosmically speaking, that is practically in our backyard. Now, I know what you are thinking. 50 light-years sounds far away. We have stars that are only 4 light-years away, and we are not worried about them crashing into us. And you are right. The odds of a rogue black hole hitting Earth directly are incredibly small. We are talking about a 1 in 1 billion chance over the entire history of the solar system. But direct impact is not the only way these things can kill us, and the other ways are much, much more likely. Let us imagine a scenario. A rogue black hole, about 10 times the mass of our Sun, is drifting through the galaxy. It has been traveling for millions of years, invisible, silent, and deadly. And its path is taking it toward our solar system. We would not detect it until it was very close. Maybe we would notice a strange distortion in the positions of distant stars as the black hole's gravity bent their light. Maybe we would see the orbits of the outer planets begin to wobble. But by then, it would already be too late. The black hole does not need to hit Earth to destroy us. It does not even need to come that close. If the black hole passes within a certain distance, close enough that the gravitational pull on the near side of Earth is much stronger than the pull on the far side, our planet would be torn apart. This is called tidal disruption, and the scientific term for what happens next is spaghettification. Earth would be stretched into a long, thin stream of debris, like a piece of spaghetti, swirling into the black hole's maw. Every mountain, every ocean, every city, every living creature, all of it would be pulled into an infinitely dense point and crushed out of existence. The odds of this happening are about 1 in 10 million over the life of the solar system. That is still very small, but it is not zero. And it is more likely than you winning the jackpot on a Powerball lottery ticket. Think about that for a second. The odds of a cosmic disaster that would tear our entire planet into spaghetti are better than the odds of you becoming a multimillionaire in a lottery drawing. But the third scenario is the most terrifying because it is the most likely. The black hole does not need to hit us. It does not need to tear us apart. It just needs to pass somewhere in the vicinity of our solar system. If a rogue black hole comes within the orbit of Jupiter, it would disturb the gravitational balance of the entire system. The orbits of all the planets would be thrown into chaos. Earth could be sent flying out of the solar system, a frozen rogue planet drifting through interstellar space. Or we could be flung into the sun, incinerated in an instant. Or we could be pulled into a new, wildly elliptical orbit that takes us from scorching heat to crushing cold every few months. Life would not survive. The oceans would boil or freeze. The atmosphere would be stripped away. And all of this would happen without the black hole ever touching us. The odds of this happening over the entire history of the solar system are about 1 in 10,000. That is not a comforting number. 1 in 10,000 means that if you had 10,000 solar systems, statistically, one of them would have its planets scattered by a passing black hole over the course of a few billion years. But here is the thing. The solar system is about 4.5 billion years old. That means we have already had our cosmic dice roll, and we are still here. But the dice keep rolling. A black hole could pass through the outer solar system tomorrow. The odds are low, but they are real. If we ever discovered that a rogue black hole was on a collision course with Earth, I honestly hope they keep it from us, because there would be absolutely nothing we could do. We have no technology to stop a black hole. We cannot deflect it. We cannot destroy it. We cannot even slow it down. We would just have to sit and wait, watching the stars distort and the sky bend, knowing that the end was coming and there was no escape. That is a special kind of horror. but it is only the beginning. Let us turn our attention to something much closer, something we see every single day. 150 million kilometers away from Earth is our biggest friend and perhaps our biggest enemy. The sun. It gives us light. It gives us warmth. It makes all life on Earth possible, but it can take it all away just as easily. And it does not need to die or explode to do it. It just needs to have a bad day. Roughly every 11 years, the sun goes through a cycle of activity. It becomes more turbulent, more chaotic, more violent. We call this the solar maximum. And here is the scary part. We have just entered a new solar maximum. Right now, as you are listening to this, the sun is becoming more active. Sunspots are growing. Magnetic field lines are twisting and snapping. And every once in a while, the sun unleashes a massive burst of energy called a solar flare or a coronal mass ejection. These are events where the sun basically sneezes. But a solar sneeze is not like a human sneeze. A solar sneeze is a cloud of superheated, magnetized plasma traveling at millions of kilometers per hour, carrying the energy of billions of nuclear bombs. And if one of these clouds is aimed at Earth, we are in trouble. The best example of this happened in 1859. An astronomer named Richard Carrington was observing a massive sunspot when he saw an incredibly bright white flash of light. It lasted only 5 minutes, but 18 hours later the effects hit Earth. Auroras appeared all over the world, even near the equator. People in the Rocky Mountains woke up in the middle of the night because the sky was so bright they thought it was dawn. Telegraph systems, the cutting-edge technology of the time, began sparking and catching fire even when they were disconnected from their batteries. The entire global telegraph network essentially melted down. That was the Carrington event, the most powerful geomagnetic storm in recorded history. Now, imagine that happening today. In 1859, the world ran on a few wires and some batteries. Today, we run on an incredibly complex, interconnected, and fragile electrical grid. If a Carrington-level event hit Earth tomorrow, we would have about 18 to 24 hours of warning. That is it. One day to shut down the entire global power grid. And we would try, but we would not be able to do it in time. The storm would arrive as a blast of charged particles slamming into our magnetosphere and distorting our planet's magnetic field. Power lines would act like giant antennas, inducing massive currents of electricity. Transformers would overload and explode. Power stations would catch fire. The entire grid would collapse, not just in one country, everywhere. The aurora would be stunning, absolutely breathtaking, the most beautiful light show humanity has ever seen. But that is where the fun stops. With the power grid down, communications would be gone. No internet, no phones, no radio. Hospitals would be running on backup generators, which would fail when their fuel ran out. Water treatment plants would stop working. Refrigeration would stop working. Within days, food would start to rot. Within weeks, millions of people would die from starvation, dehydration, or exposure. In cold climates, people would freeze in their homes. In hot climates, people would die from heat stroke. The most developed countries in the world would be reduced to a pre-industrial existence in a matter of hours. And rebuilding would take years, if not decades. The damage from a Carrington-level solar storm today is estimated in the trillions of dollars. And it is not a matter of if, it is a matter of when. We know that these storms happen. We know they are a natural part of the sun's cycle. And we know that we are overdue for a big one. The last truly massive storm was 1859. That is over 160 years ago. The statistical probability suggests we will face another one this century. It could happen next year. It could happen next month. It could happen tomorrow. But as terrifying as that sounds, I need to be honest with you. In the grand scheme of cosmic destruction, a solar storm is almost comforting. It is a natural disaster, something we understand, something we can prepare for, even if we probably will not. The next ways Earth could be destroyed are on a completely different level. They are not just planetary, they are galactic, and the one after that, universal. Let us go back to the 1960s, the height of the Cold War. The United States, the Soviet Union, and the United Kingdom are all pointed nuclear weapons at each other. They are testing bombs in the atmosphere, in the oceans, underground. Things are getting out of control. So, in 1963, they signed the Partial Test Ban Treaty. They all agree to stop detonating nuclear weapons in the atmosphere and in outer space. But how do you verify that? How do you trust that the other side is keeping its promise? The United States decides to find out. They launch a series of satellites called Vela. The name comes from the Spanish word for watchman. Their job is to watch for nuclear explosions. They are equipped with sensors designed to detect the X-rays and gamma radiation that a nuclear bomb would release if detonated in the atmosphere. The Vela satellites did their job. They never found any evidence of Soviet nuclear tests, but they found something else, something completely unexpected. On July 2, 1967, both Vela satellites detected a massive spike of gamma radiation. It came from deep space, not from Earth. The scientists were confused. They had no idea what could produce such a powerful burst of energy from outside the solar system. They waited, and it happened again and again. By 1973, they had recorded 16 of these mysterious events. They called them gamma-ray bursts. For 2 decades, no one knew what caused them. There were theories, wild guesses, speculation about alien technology, or unknown cosmic phenomena. It was not until the 1990s that we finally figured it out. And the answer was terrifying. Gamma-ray bursts are caused by 2 things: either 2 neutron stars merging together in a cataclysmic collision, or a massive star collapsing into a black hole, a process we call a core collapse supernova. When a star many times heavier than the Sun runs out of fuel, its core collapses. The outer layers of the star fall inward at incredible speeds. And as the core collapses into a black hole, powerful magnetic fields form, funneling some of the star's material into 2 narrow beams. These beams shoot out from the poles of the collapsing star at nearly the speed of light. They are composed of plasma, gamma rays, electrons, and their antimatter counterparts, positrons. In less than a single second, a gamma-ray burst releases as much energy as our Sun will produce over its entire 10 billion-year lifetime. 10 billion years of solar output in 1 second. That is the power we are talking about. These bursts are so bright that we can detect them from billions of light-years away. They are the most energetic events in the universe since the Big Bang itself. And if one of these beams were aimed directly at Earth, we would not stand a chance. A gamma-ray burst within 200 light-years of Earth that makes a direct hit would vaporize our planet. The atmosphere would be ionized, the ozone layer would be stripped away, high-energy radiation would rain down on every living thing. It would be a slow and painful death, for anything that survived the initial blast. But here is the part that people often get wrong, and it is important to clarify this because the odds are very different from what you might assume. Many people think gamma-ray bursts are incredibly rare, almost impossibly rare. And it is true that a direct hit from a gamma-ray burst aimed at Earth is a low-probability event. But here is the correction that matters. Gamma-ray bursts themselves are not rare. They happen all the time. We detect gamma-ray bursts every single day, multiple times a day, in fact. The universe is constantly producing these death beams. Most of them are so far away that they pose no threat. But the fact that they are common means that the potential for one to occur relatively close to us is not as low as you might think. The universe is crowded with massive stars, and massive stars die all the time. The Milky Way galaxy alone contains hundreds of millions of stars massive enough to produce a gamma-ray burst when they die. Statistically, a gamma-ray burst should occur in our galaxy about once every 100,000 to a million years. That sounds like a long time, but on a cosmic scale, it is not. And when you consider that we have been around as a species for only a few 100,000 years, it becomes clear that we are overdue for a local event. And it gets worse. It has happened before. 440 million years ago, during the Ordovician period, Earth experienced the second largest mass extinction in its history. Only the dinosaur-killing asteroid impact at the end of the Cretaceous was more devastating. 85% of all species on Earth vanished. For decades, scientists were not sure what caused it. But a leading theory is that a gamma-ray burst was responsible. A hypernova, a star collapsing into a black hole, occurred about 6,000 light-years away from Earth. The beam was pointed in our direction. It lasted just 10 seconds, but 10 seconds was enough. Half of Earth's ozone layer was destroyed immediately. Ultraviolet radiation from the sun, normally filtered out by the ozone, poured through the atmosphere like a cosmic blowtorch. The surface of the ocean became toxic. Plankton died. The entire marine food chain collapsed. Species that could not find shelter from the radiation went extinct. It was a slow, grinding catastrophe that took hundreds of thousands of years to play out. And it was all caused by a flash of light that lasted less time than it takes to tie your shoes. Researchers who study this theory estimate that an extinction-level gamma-ray burst should occur at least once every billion years or so. That means the average probability for any given year is about 1 in a billion. That is low. But remember, that is an average. The universe does not schedule these things neatly. A gamma-ray burst could happen tomorrow. It could happen 6,000 light-years away, and the beam could be aimed directly at us, and we would never know until the radiation arrived at the speed of light. We would have no warning, no time to prepare, no time to say goodbye. 1 second, everything is normal. The next second, the sky lights up with a flash brighter than 1,000 suns, and the Earth begins to die. There is no shelter, no bunker, no technology that can protect you from a gamma-ray burst at close range. It is the end, and it is instantaneous. But even that, as unimaginable as it is not the most terrifying way the Earth could be destroyed tomorrow. Because gamma-ray bursts, solar storms, and rogue black holes are all events that happen within the universe. They destroy planets and life, but the universe itself continues. The laws of physics remain the same. Gravity still works, Atoms still hold together. There is still a universe left for whatever remains. The final method on our list does not leave a universe behind. It destroys everything. Every galaxy, every star, every planet, every atom, every particle, every law of physics, every possible reality, gone in an instant, and it could happen at any moment. This is called false vacuum decay, and I am going to explain it in the simplest way possible, because it is not as complicated as people make it sound. The key is understanding that everything in the universe wants to be in its lowest possible energy state. Think of it like a ball rolling down a hill. The ball will naturally come to rest at the bottom of the hill, the lowest point it can reach. That is a stable state. But what if the bottom of the hill is not actually the bottom? What if there is a deeper valley hidden underground? The ball is sitting in a little dip on the side of the mountain. It looks stable. It feels stable, but it is not the true ground state. It is a false vacuum. And if something comes along and nudges that ball just enough, it will fall through the false bottom and tumble all the way down to the real bottom. In our universe, the Higgs field is responsible for giving all particles their mass. The Higgs boson, discovered in 2012 at CERN, is the particle associated with this field. And according to our current best models of physics, the Higgs field might be in a false vacuum state. It looks stable. It has been stable for 13.8 billion years, but it might not be the true lowest energy state. There could be a deeper, more stable state that the Higgs field has not yet reached. If a small region of the Higgs field somewhere in the universe were to tunnel through a quantum barrier and fall into that true vacuum state, it would create a bubble, and that bubble would expand outward at the speed of light. Inside the bubble, the laws of physics would be different. The Higgs field would have a different value. Particles would have different masses. Atoms might not be able to form. Chemistry might not work. Life, as we know it, would be impossible. Everything that exists inside the bubble would be annihilated, not by an explosion, but by a fundamental change in the very fabric of reality. The bubble would grow at the speed of light. That means we would have no warning. No signal can travel faster than light. The moment the bubble reaches Earth, we would simply cease to exist. Not in a violent flash, not in a fiery explosion. We would just be gone. The atoms that make up your body would no longer be able to exist. The universe would be completely and utterly different, and there would be nothing left to observe it. Now, here is the context that many viewers have asked for. Is false vacuum decay real? We do not know for certain. Our current models suggest that the Higgs field is in a metastable state, meaning it could decay, but the probability is incredibly low. The universe has survived for 13.8 billion years without decaying, so the odds of it happening tomorrow are astronomically small. But here is the thing that should make you pause. We have no idea if false vacuum decay has already occurred elsewhere. Think about that. There could be a bubble of true vacuum expanding toward us right now, traveling at the speed of light, and we would never know until it arrived. It could have started a billion years ago in a distant galaxy. It could be halfway here. It could be 1,000,000 light years away. Or it could have started yesterday, a few 100,000 light years away. We have no way of knowing. No telescope can see it coming. No instrument can detect it, because it travels at the speed of light, and nothing can outrun it. It is the ultimate blind spot. We are living in a cosmic waiting room, and the buzzer could go off at any second. Some physicists have even speculated that false vacuum decay might already be happening inside the Large Hadron Collider at CERN. Every time we smash particles together at near-light speeds, there is a tiny, almost impossibly small chance that we could create a bubble of true vacuum. Most scientists say this is not a real risk, that high-energy cosmic rays have been hitting Earth at even higher energies for billions of years without causing a vacuum decay. They are probably right, but probably is not a comforting word when the alternative is the end of the universe. So, what do we do with all of this information? How do we live knowing that at any moment, a rogue black hole could tear our planet apart, a solar storm could plunge us into the dark ages, a gamma-ray burst could sterilize the surface of the Earth, or the fundamental fabric of reality could simply unravel? The honest answer is that we do not do anything. There is nothing to do. We cannot prepare. There is no survival strategy, no bunker deep enough, no plan clever enough. The universe is vast and violent and utterly indifferent to our existence. That is not a reason to despair. It is a reason to appreciate what we have. Every day that the sun rises, every day that the planet stays intact, every day that the laws of physics remain stable, is a gift, a fragile, temporary, precious gift. The odds are overwhelmingly in our favor that none of these events will happen tomorrow. The universe is big and empty, and most of the time, things just go on as they always have. But the possibility is always there. The dice are always rolling, and maybe that is the most terrifying thing of all. Not the destruction itself, but the uncertainty, the knowledge that there are forces beyond our control, beyond our understanding, beyond our imagination, that could snuff us out in an instant. We are not the masters of our fate. We are passengers on a tiny blue planet, hurtling through a dangerous cosmos, and we have no idea what tomorrow will bring. But perhaps that uncertainty is exactly what makes life worth living. We spend our days worrying about things we can control: jobs, relationships, money, the petty grievances that fill our news feeds. And yet, beneath all of that noise, there is this silent, cosmic backdrop, a stage that could collapse at any moment. The rogue black holes, the solar flares, the gamma-ray bursts, the false vacuum decay. They are not threats we need to prepare for in any practical sense. They are reminders. They remind us that the universe does not owe us tomorrow. It does not owe us a single breath. Every second that the Earth continues to spin, every second that the sun continues to shine, every second that the Higgs field remains in its metastable state, is borrowed time, and we are borrowing from a lender who can call in the debt at any instant. So, what do we do with that knowledge? We do not build bunkers. We do not stockpile canned food. We do not form committees to plan for the end of reality, because all of that would be meaningless. What we can do is live, truly live, not in a frantic, desperate way, but with an awareness that this moment, right now, is fragile. The people you love, the laugh you just shared, the warmth of the sun on your skin, they are not guaranteed. The universe is a chaotic, violent, beautiful place, and we are here against all odds for a fleeting instant. The same forces that could destroy us tomorrow are the forces that created us in the first place. The supernovae that seeded the cosmos with heavy elements, the stable fusion of our sun, the precise tuning of the laws of physics, they all had to align perfectly for you to be reading these words, and they could unalign just as easily. That is not a reason to be afraid. It is a reason to be grateful. Every day without a gamma-ray burst is a win. Every night, the stars remain in their familiar patterns is a blessing. Every breath you take is a small miracle in a universe that is, on its grandest scales, utterly indifferent. So, go outside, look up at the sky. Know that the darkness above you is filled with invisible monsters, wandering black holes, dying stars, fields of energy that could rewrite reality. But also, know that you are alive. Right now, in this moment, you exist. And existence is the rarest, most precious thing in all of creation. And if the Earth is destroyed tomorrow, well, at least you had today. The universe may be a mean place, but it is also our home. And as long as we are here, we have the power to wonder, to love, and to imagine what lies beyond. So, cherish this fragile existence. For in the end, the only way to face the void is to hold each other close and keep looking up. The end of all life on Earth in 2 hours. Not in a million years, not over centuries of slow decline, but before the sun sets on a single day. It sounds like the premise of a disaster movie, the kind where heroes scramble to save the world in the final act. But the reality is stranger and more unsettling than fiction, because the physics that could make this happen is real, and it demands no villain, no warning, and no last-minute rescue. What we're going to explore tonight are the scenarios, backed by known science, not speculation, that could sterilize this planet completely. Not just kill most humans, not just trigger a mass extinction that wipes out 90% of species, but erase every living thing from the surface, from the deep ocean, from the rock kilometers underground. And in some of these scenarios, the process from first trigger to final silence takes less than the time it takes to watch a movie. Before we go any further, a quick note on scale. When people hear end of all life, they tend to imagine something like the asteroid that killed the dinosaurs 66 million years ago. That event was catastrophic. It wiped out 3/4 of all species, but it did not end life. Cockroaches survived, scorpions survived, bacteria in every crevice of the planet survived. The dinosaurs were gone, but life itself carried on, eventually leading to us. So, when we say all life, we mean everything. The microbes living 3 kilometers deep in solid rock, the heat-loving archaea at hydrothermal vents on the ocean floor, the spores that can survive vacuum and radiation. To kill every last one of them requires something fundamentally different from a mere mass extinction. It requires the planet itself to become uninhabitable at every possible refuge. Let's start with the scenario that most people think of first, an asteroid. But not just any asteroid. The Chicxulub impactor was about 10 to 15 kilometers across. That's roughly the height of Mount Everest, moving at 20 kilometers per second. To put that speed in terms we can grasp, it covers the distance from New York to Los Angeles in about 200 seconds, just over 3 minutes. At that velocity, the air in front of the asteroid compresses so violently that it heats to 50,000 degrees, 9 times hotter than the surface of the sun. The impact itself releases energy equivalent to 100 teratons of TNT. That number is so large, it's almost meaningless. So let's break it down. The Hiroshima bomb released about 15 kilotons. 100 teratons is 100 trillion tons of TNT. That is roughly 6,700,000,000 Hiroshima bombs, all going off in the same instant, in the same spot. The crater left behind is 180 kilometers across. You could walk around its rim for 3.5 weeks without stopping. But even with that unimaginable energy, Chicxulub did not sterilize the planet. The global firestorm that followed, from debris re-entering the atmosphere and heating the air to oven temperatures, killed most surface life within hours. The impact winter that followed, caused by soot and sulfur in the stratosphere, starved the survivors over months. Yet life found a way. Small mammals, birds, insects, and deep-sea organisms persisted. The planet was reset, not erased. So what would it take to actually erase everything? The answer is an impactor roughly 500 kilometers across. That's 2/3 the size of Ceres, the largest object in the asteroid belt. Nothing that big is on a collision course with Earth today. The stable orbits of large asteroids are well understood, but the physics of what such an impact would do is not hypothetical. About 3.9 billion years ago, during the late heavy bombardment, the Earth was repeatedly hit by objects large enough to vaporize the entire ocean, not just heat it, not just boil the top layer, but turn the entire ocean into steam. Once the ocean turns to steam, the greenhouse effect becomes self-sustaining. The steam traps heat, which evaporates more water, which traps more heat, until the surface temperature exceeds the boiling point of rock. That process takes time, days to fully play out. But within the first 2 hours after such an impact, the global temperature would already be above the lethal limit for any known organism. The bacteria deep in the rock would be cooked as heat slowly conducts downward over centuries. The planet would become a sterile Venus-like world. And here is the crucial point about the 2-hour window. The initial explosion, the global heat pulse from falling debris, and the onset of runaway evaporation all happen within that first 120 minutes. A person standing on the surface on the opposite side of the planet would see nothing for about 20 minutes. Then the ground would shake with an earthquake that dwarfs anything in recorded history. About an hour later, the sky would begin to glow as re-entering debris heats the atmosphere. Within 2 hours, the air itself would become hotter than a pizza oven. Everywhere, not just near the impact site. Water would boil in puddles. Animals would die from thermal shock. Plants would ignite. The surface would become a world of fire and steam. And that is only the beginning. Let's shift our attention to a different kind of threat, one that comes not from a rock in space, but from a flash of light from across the galaxy, a gamma-ray burst. These are the most energetic explosions in the universe, occurring when a massive star collapses into a black hole, or when two neutron stars collide. In a matter of seconds, a gamma-ray burst releases more energy than our sun will produce in its entire 10 billion-year lifetime. The energy is focused into two narrow jets that travel at 99.9% of the speed of light. If one of those jets were pointed at Earth from within about 6,000 light-years, the consequences would be immediate and devastating. The gamma rays would hit our upper atmosphere without warning. They would strip electrons from molecules, triggering a cascade of chemical reactions that would destroy the ozone layer within minutes. Without ozone, ultraviolet radiation from the sun would bombard the surface at levels 100 times greater than normal. Phytoplankton, the microscopic organisms in the ocean that produce half of Earth's oxygen, are extremely sensitive to UV. A massive UV spike would kill them within weeks. Since phytoplankton form the base of the ocean food web, the entire marine ecosystem would collapse. On land, insects, which are essential for pollination and soil health, would die in enormous numbers. Small mammals and birds without thick fur or feathers would suffer fatal sunburn and DNA damage. The surface would become a desert of death. Would a gamma ray burst sterilize the entire planet? Probably not. Organisms living kilometers underground or deep in the ocean would be shielded. Bacteria in rock, extremophiles at hydrothermal vents would survive. A gamma-ray burst would cause a mass extinction rivaling the worst in Earth's history, but it would leave a biological seed. That said, if the burst were extremely close, within a few hundred light years, the direct gamma radiation itself could be intense enough to penetrate the atmosphere and kill even buried organisms. But such a close burst would require a massive star very near us, and there are no candidates in our immediate neighborhood. The risk is real, but for now, remote. Now, we come to the most exotic and absolute scenario: vacuum decay. This is not a theory from science fiction. It is a real prediction of quantum field theory. The vacuum of empty space is thought to be in a metastable state, like a ball resting in a shallow dip on a hill. It is stable unless something gives it a kick over the edge. If that kick happens, the vacuum would decay into a lower energy state, and the laws of physics themselves would change. Inside a bubble of this new vacuum, the fundamental constants, the mass of the electron, the strength of electromagnetism, the nature of nuclear forces would be different. Atoms would not hold together. Chemistry would cease. Everything we know as matter would dissolve. The bubble would expand outward at the speed of light. There would be no warning, because the bubble travels at the same speed as any signal from it. The moment you could see it coming is the moment it arrives. And in that instant, every atom in your body is converted to something else, something that cannot sustain life, thought, or structure. The time it takes for the bubble to cross the Earth is about 40 milliseconds. That is less than a blink. In 2 hours, the bubble would have expanded across the solar system and beyond. But for Earth, it is over in a fraction of a second. Vacuum decay is the ultimate sterilizer because it doesn't just kill life, it erases the physical substrate that made life possible. We should pause here and note a recurring theme. Many of the scenarios that could end all life operate on timescales that are breathtakingly short at the moment of impact, but the full sterilization may take longer. The key is that the trigger happens within minutes or hours, and after that, recovery is impossible. Even if the immediate death toll is not complete in 2 hours, the trajectory toward total extinction is locked in. Another candidate, a magnetar flare. Magnetars are neutron stars with magnetic fields 1 trillion times stronger than Earth's. If one were as close as the Moon, its magnetic field would rip the iron from your blood. In 2004, a magnetar 50,000 light-years away erupted with a flare that briefly ionized Earth's upper atmosphere from across the galaxy. If that same flare occurred from a distance of 10 light-years, it would strip away a substantial part of our atmosphere. From 1 light-year, it would be catastrophic. The first 2 hours would see the ozone layer destroyed, the surface flooded with lethal radiation, and the atmosphere heated to extreme temperatures. Again, some deep subsurface life might survive if the pulse is brief, but a close magnetar flare could push the planet into a runaway state similar to the impact scenario. Let's now consider something that is not astronomical but biological: an engineered pathogen. The tools of genetic engineering have advanced so rapidly that a skilled researcher could, in theory, design a virus with the transmissibility of measles and the lethality of something far worse. Such a pathogen could spread across the globe within weeks, killing billions. But would it end all life? No. Bacteria would survive. Most insects would survive. Plants would survive. The deep biosphere would be untouched. An engineered pandemic could end human civilization, but it cannot sterilize the planet. The sheer diversity and resilience of life, from extremophiles in boiling springs to bacteria in Antarctic ice, means that any biological agent has a hard limit. It cannot reach organisms living in rocks, in hydrothermal vents, or in the deep ocean abyss. What about a runaway greenhouse effect, like the one that turned Venus into a hellish world? Earth is currently far from that threshold, but if something, a massive impact, a nearby supernova, a sustained increase in solar output, pushed global temperatures above 70 or 80 degrees Celsius, the feedback loop could begin. Water vapor would trap heat, causing more evaporation, causing more heat. The ocean would start to boil. Steam would rise into the upper atmosphere, where ultraviolet light would split it into hydrogen and oxygen. The hydrogen would escape to space, and the water would be lost. This process takes millennia, not hours. But the trigger, the initial shove over the tipping point, could happen in 2 hours. And once started, it cannot be stopped. The planet would become a sterile, dry, hot rock. We also have to consider the possibility of a rogue black hole. The galaxy contains an estimated 100 million stellar mass black holes, drifting invisibly through space. If one passed within a few million kilometers of Earth, the tidal forces would trigger earthquakes, volcanic eruptions, and tsunamis on a scale never seen. The planet would be yanked from its orbit, possibly thrown into a region too hot or too cold for life. A close passage, within a few thousand kilometers, could literally tear the crust apart. The time from first detectable perturbations to full catastrophe would be measured in hours. The black hole itself might not consume the planet, but the orbital disruption would end all life. Now, let's address the criticisms that often arise when people hear these scenarios. Some argue that all life destroyed is an overstatement because cockroaches and tardigrades have survived mass extinctions. That is true for extinction events. But the scenarios we are describing are not extinction events. They are sterilization events. The difference is crucial. Cockroaches survived the Chicxulub impact because they could hide underground, feed on detritus, and wait out the darkness. But they cannot survive the complete vaporization of the ocean or the breakdown of the ozone layer to the point where lethal UV penetrates every crevice. They cannot survive the boiling of every surface water source. They cannot survive the heat pulse that raises rock temperatures to over 100 degrees for thousands of years. So, when we say all life, we mean it literally. The improvement insights from viewers of similar videos highlight the need for clearer explanations of large numbers and more focused structure. So, let's fix that now. The energy from a 500-kilometer asteroid impact is roughly 3 times 10 to the 30th joules. That is equivalent to the Sun's total energy output over 8 minutes. That is not a number you can visualize directly, but you can visualize this. The Hiroshima bomb was about 63 trillion joules. The impact would release about 50 billion times that energy. If you stack Hiroshima bombs end to end, 50 billion of them would stretch from Earth to the Moon and back 100 times. That's the scale of what we're talking about. And yet, even that does not guarantee instantaneous sterilization. It takes hours for the heat to spread, days for the ocean to boil, years for the underground to cook. The 2-hour mark is when the surface becomes utterly lethal and the trajectory toward total extinction becomes inevitable. Why does the 2-hour window matter? Because it is the time it takes for the first irreversible step to be completed. In the impact scenario, 2 hours after impact, every exposed organism on the surface is dead. The atmosphere is superheated, the sky is glowing, and the oceans are starting to steam. In the gamma ray burst scenario, within 2 hours the ozone layer is gone, and the UV levels are already deadly. In the vacuum decay scenario, it's all over in 40 milliseconds. In the Magnetar flare scenario, the initial radiation pulse arrives in minutes, and the cascading atmospheric effects unfold over the next couple of hours. 2 hours is the point of no return for the planet's biosphere. But let's not get lost in the most extreme possibilities. The most immediate threats to complex life, including our civilization, are not these cosmic cataclysms. They are self-generated: nuclear war, climate change, engineered pandemics, and the potential misalignment of artificial intelligence. None of those would sterilize the Earth, but they could end human civilization and cause a mass extinction that takes millions of years to recover from. The distinction is vital because the cosmic threats are beyond our control. We cannot deflect a 500-kilometer asteroid if we have only a few years of warning. We might not even see it coming. We cannot stop a gamma-ray burst, but we can prevent a nuclear exchange. We can reduce carbon emissions. We can regulate biotechnology. These are choices we make, not random acts of the universe. Think about the psychological trap we fall into. Humans are terrible at assessing low-probability, high-impact risks. We worry about plane crashes because they are dramatic, but we ignore slow-moving disasters. The chance of a planet-sterilizing event occurring in any given century is astronomically low, perhaps 1 in a billion or less. The chance of a civilization-ending event from our own actions in the next 100 years is far higher, maybe 1 in 100 when you consider nuclear and environmental risks. Yet we spend more money on asteroid detection than on pandemic prevention, and more on defense than on climate adaptation. The expected value, the product of probability and consequence, is higher for the self-generated threats. They deserve more of our attention precisely because we can do something about them. Let me describe what the first 2 hours of a planet-sterilizing event would feel like if you were unlucky enough to be on Earth. Choose the ocean vaporizing impact scenario. You are on a remote beach in the Pacific, far from the impact site on the other side of the globe. For the first 20 minutes, everything seems normal. The sun is shining, the waves are rolling in. Then the ground begins to tremble, not like an earthquake, but a sustained shaking that grows stronger and stronger. You cannot stand. Buildings collapse in the distance. The ocean recedes, then surges back in a wave hundreds of meters high. But you do not see the wave because before it arrives, the sky starts to glow. First orange, then white. The heat becomes unbearable. You feel like you're standing inside an oven. Your skin blisters in seconds. The air itself is on fire. You cannot breathe. Within minutes, you are gone. Every exposed organism on the entire planet goes through the same experience simultaneously. Those in caves, in deep burrows, survive a bit longer, an hour, maybe 2. But the thermal pulse eventually reaches them as the rock heats up. By the 2-hour mark, the surface is a sterile wasteland. What about the survivors that we mentioned earlier? The bacteria deep underground? They are not dead yet. The rock is a good insulator. It will take years for the heat from the surface to penetrate kilometers down, but eventually it will. The temperature will rise above the tolerance of even the most hardy extremophiles, around 130 degrees Celsius. Once that happens, every bacterium, every archaeon, every dormant spore will be cooked. The timeline for complete sterilization could be decades or centuries, but the process is irreversible. The planet will remain hot for millions of years. No life will return unless it evolves from scratch, which would take another billion years or more. Now, I want to address a common question. Why haven't we seen evidence of such an event in the fossil record? Because the fossil record is a tiny and biased sample of Earth's history. The late heavy bombardment, 3.9 billion years ago, likely came close to sterilizing the planet multiple times. The geological evidence from that period is almost entirely erased by plate tectonics. We know that large impacts occurred because we see the scars on the moon. But on Earth, those craters have been recycled. It is entirely possible that life was reduced to a single refuge, a deep hydrothermal system or a rock pocket, and then expanded again. That would explain why all life on Earth shares a common biochemistry. We may be descendants of survivors who clung to existence by the thinnest of margins. Let's step back and appreciate the perspective that these scenarios give us. Life on Earth is 4 billion years old. It has survived ice ages, asteroid impacts, volcanic winters, and the gradual brightening of the sun. It is not fragile. The deep biosphere, the kingdom of microbes living in rock, is so widespread and resilient that fully sterilizing the planet requires an event that reshapes the planet itself. That is why every mass extinction in history, even the one that killed 96% of species, left life intact. The planet has never been fully sterilized in the last 4 billion years, but that does not mean it never will be. The universe is vast and indifferent, and the physics of extinction are clear. Given enough time, billions of years, a planet-sterilizing event is not just possible, but probable. The sun itself will eventually brighten enough to trigger a runaway greenhouse on Earth in about 1 billion years, regardless of anything we do. That is a long time from now, but it is finite. For now, the cosmic threats are remote. The threats we face from our own hands are immediate, and that is the most important takeaway. The scenarios that could end all life in 2 hours, the ocean vaporizing impact, the ultra-close gamma-ray burst, the vacuum decay bubble, the Magnetar flare, are real possibilities, but they are not the most urgent. The most urgent are the ones we can influence: nuclear war, climate change, engineered pathogens, and the mismanagement of powerful technologies. These threats will not end all life, but they could end our civilization, and they could cause suffering on a scale that dwarfs anything in history. We have the ability to prevent them. That ability is our greatest asset and our greatest responsibility. The story of life on Earth is not yet finished. We are the first species to understand the forces that could unmake us, and that understanding gives us a choice. We can spend our time worrying about the unlikely but dramatic cosmic threats, or we can focus on the likely but less dramatic self-inflicted ones. The wise path is to do both, to invest modestly in planetary defense and monitoring, while investing heavily in reducing the dangers we create ourselves. The end of all life on Earth in 2 hours is possible, but it is not probable in our lifetimes. The end of our civilization in a few decades is more probable, and that is a future we can still change. In closing, remember that life is not a passive passenger on a rock. It alters the planet, and the planet alters it. We are part of that dance, and we have, for the first time, the ability to choose the next steps. Whether we choose wisely or not will determine whether the story continues, not just for humans, but for the entire biosphere that gave rise to us. The universe will go on either way, but we have the chance to make sure that, for now, life does too. We have the chance to make sure that, for now, life does too. But let's not mistake that chance for a guarantee. The geological record is a testament to the fact that life has been pushed to the edge before. The Permian extinction, the Great Dying, saw an estimated 96% of marine species disappear. The planet came within a hair's breadth of complete collapse. What saved the remaining 4%? Not intelligence, not foresight, just luck. A few pockets of anoxic ocean, a few heat-tolerant organisms, a few deep-sea vents that kept pumping out energy. Life clung on because the extinction was not quite total. The difference between that event and the ones we have described, the ocean vaporizing impact, the ultra-close gamma-ray burst, is the difference between a near miss and a direct hit. In the Permian, the planet remained habitable for microbes. In a sterilization event, it does not. So when we talk about the end of all life, we are talking about extinguishing not just the visible world, the forests, the coral reefs, the herds of animals, but the invisible foundations on which everything rests. To kill a bacterium living 3 kilometers underground, metabolizing hydrogen from rock, you have to heat its entire environment to over 130 degrees Celsius and keep it there for years. That requires a global energy input so massive that it redefines the planet itself. The Chicxulub impactor, for all its destruction, deposited about 100 teratons of energy. That is a number that boggles the mind, 100 trillion tons of TNT. But to heat the entire crust to sterilization, you need tens of thousands of times that energy. That is why no known event in the last 4 billion years has fully sterilized Earth. The gap between survivable and total is enormous. Now, consider the emotional weight of that realization. It can be comforting. Life is tough. Or it can be sobering. The only events that can truly end everything are those that dismantle the planet itself. And those are events we cannot prevent. They are not like a pandemic we can vaccinate against or a nuclear war we can negotiate away. They are the raw violence of the universe. A supernova within 30 light years, a passage of a rogue black hole, a gamma ray burst from a nearby hypernova. These are not hypotheticals. They are inevitable somewhere, sometime. The only question is whether Earth happens to be in the wrong place at the wrong time. And yet, there is another category of threat that we often overlook, one that is both more plausible and more subtle. It is the slow, cumulative degradation of the planet's life support systems. Not a single catastrophe, but a cascading series of smaller failures, each amplifying the next. Imagine a world where the Amazon rainforest dries out and burns, releasing billions of tons of carbon. That warming melts the permafrost, releasing methane, which causes more warming. The warming disrupts ocean currents, causing the collapse of fisheries. The collapse of fisheries triggers a global food crisis. The food crisis leads to conflict, which weakens international cooperation, which makes it harder to respond to the next crisis. This is not a science fiction scenario. It is a plausible trajectory if we continue on our current path. What would that world look like after 2 hours? Nothing dramatic. The sun would still shine, the birds would still sing for a while, but the underlying system would be fraying. The biosphere would be losing resilience. Each species that goes extinct weakens the web. Eventually, the web snaps, not in a single moment, but over decades. And when it snaps, what remains is not a sterile planet, but a depleted one. A world with fewer fish, fewer insects, fewer forests, less oxygen. A world where complex life, including us, can no longer sustain itself. That is not the same as all life ending, but for a species that depends on complex food webs, it might as well be. The reason this matters is not to frighten you, but to clarify where our focus should lie. The cosmic events that could end all life in 2 hours are real, but they are rare. The self-inflicted events that could end civilization as we know it are far more likely. And unlike the cosmic events, we can do something about them. We can decarbonize our economy. We can strengthen global health systems. We can reduce nuclear arsenals. We can safeguard biodiversity. We can build the institutions and norms that make cooperation possible. These are not impossible tasks, they are choices. Let me put it in perspective with numbers that are easier to grasp. The probability of a civilization-ending asteroid impact in the next century is roughly 1 in 10,000 to 1 in 100,000. That is a very small number. The probability of a civilization-altering pandemic in the next century is arguably close to a certainty. The question is only when and how severe. The probability of catastrophic climate disruption that destroys food production for a decade is maybe 1 in 3 to 1 in 10 over the same period. Which of these should we prioritize? Not the asteroid, as important as detection is. We should prioritize the threats that are both likely and addressable. Yet our attention is often captured by the spectacular, the cinematic, the thing that would make a great movie. A gamma-ray burst is dramatic. A supernova is dramatic. The slow unraveling of the biosphere is not dramatic. It is a series of incremental losses that accumulate over a lifetime. You do not wake up one morning to a sterile Earth. You wake up to a world that has slightly fewer butterflies, slightly less ice, slightly more empty ocean. And then you get used to it, because the baseline shifts. Each generation forgets what was lost. That is the tragedy of the slow extinction. It is happening in plain sight, and we are barely registering it. But there is a counterforce. We are capable of foresight. We are capable of collective action. We have done it before. The Montreal Protocol to protect the ozone layer, the global effort to eradicate smallpox, the reduction of nuclear arsenals from Cold War peaks. These show that when the threat is clear and the will exists, humanity can change course. The challenge is that the threats we face now are more diffuse, more interconnected, and more politically contentious. They require not just technical solutions, but a shift in values, a recognition that our survival depends on the health of the entire biosphere, not just our own species. So, let me end with a thought that ties everything together. The end of all life on Earth in 2 hours is a real possibility, but it is not the most likely. The most likely end of the world as we know it will be slower, quieter, and more out of negligence than malice. It will be the result of 1,000 small decisions, each seemingly harmless, that compound into a catastrophe. The asteroid we do not see coming, the pathogen we do not prepare for, the emissions we do not curb, the biodiversity we do not protect. We are not helpless victims of the cosmos. We are the first species in 4 billion years that has the power to choose whether to continue or to collapse. That power is terrifying, but it is also a gift. Use it wisely. Use it wisely. Because the story of life on Earth is not written in stone. It is written in the choices we make every day. The universe does not care if we survive. The planet does not care. Only we care. And that caring, that stubborn refusal to let the lights go out, is what separates a living world from a sterile rock. In 2 hours, everything could end. But in 2 hours, we can also decide to keep fighting. The clock is always ticking. What we do with the time we have is the only thing that matters.
What if the colors we see in the night sky are just the beginning of a story yet to be told? Our documentary invites you on a journey of discovery, where each chapter unfolds the hidden narratives of distant worlds, challenging what we thought we knew about our universe. First, we dive into the azure depths of Neptune, revealing its true colors. A world far beyond our own, where the winds howl with ferocity and the skies tell tales of ancient ice and gas. What mysteries does this distant giant hold in its cerulean hues? Then we venture to the enigmatic Saturn, where atop its north pole a geometric marvel, the hexagonal storm, defies explanation. What forces of nature sculpt this bizarre phenomenon? Can we unlock the secrets of Saturn's hexagonal riddle? Our odyssey continues as we seek the latest real images of Uranus. This elusive ice giant, shrouded in mystery, reveals new truths through the eyes of modern exploration. What will we discover in the unseen details of its atmosphere and rings? Finally, we journey with Chandrian 3 to our celestial neighbor, the Moon. Here in the silence of the lunar surface, the mission uncovers sights unseen by human eyes. What did Chandrian 3 witness on the Moon? What secrets lie in the dust and craters of our closest companion in space? Join us as we traverse the cosmos seeking answers and marveling at the beauty of the universe. This is not just a journey through space, it's an exploration of the unknown, a quest for knowledge, and a tribute to the human spirit's unending curiosity. Welcome to our documentary series, where the mysteries of the universe unfold before your eyes. In the vastness of our solar system, beyond the belt of asteroids and gas giants, lies a world shrouded in mystery. Neptune, the 8th planet from our Sun, a distant ice giant, has long captured our imagination. For decades, we've imagined it as a dark blue sphere at the edge of our cosmic neighborhood. But what if the vision of this distant world was an elaborate illusion? This mysterious planet, named after the Roman god of the sea, has hidden its true colors from us. Cloaked in a shroud of deep blue, Neptune has been the subject of many stories and scientific investigations. But recent discoveries have removed this azure facade, revealing a reality far more complex and fascinating than we could have imagined. For years, our telescopes have been pointed at this distant giant, capturing its essence in pixels and data. What we saw, however, was not the reality of the planet, but a reflection of our own technological and perceptual limitations. The deep blue color we associated with Neptune was actually the result of our own interpretations and enhancements, a story we unwittingly created and believed. Today, we invite you to explore Neptune like never before. Delve into its true colors, understand its dynamic atmosphere, and unravel the secrets of its moons and rings. For centuries, Neptune was portrayed as a dark blue world whose color reflected its cold, distant nature in the solar system. This representation, deeply ingrained in our collective consciousness, has become the cornerstone of our understanding of this icy giant. But what if this image was a reflection of our perceptions rather than the planet's true appearance? Neptune's color is a story of scientific evolution and the search for truth. It begins with a Voyager 2 probe launched by NASA in 1977. Sent to the outer reaches of the solar system, it took the first close-up images of Neptune, painting a picture of the planet awash in a stunning blue color. However, these images were not a direct window into the true color of Neptune. In fact, they were interpretations, the result of processing the data through the lens of human understanding and the technological capabilities of the time. The deep blue color we saw was the product of enhancements made by scientists to emphasize certain features of the planet. This story began to unravel with the advent of more advanced telescopes, such as the Hubble Space Telescope and the Very Large Telescope. These instruments, equipped with state-of-the-art technology, allowed astronomers to see the true color of the planet again. The results of this study were striking. The new images revealed that Neptune's color was not the previous deep blue, but rather a more muted and varied shade. This discovery was not just aesthetic, but a fundamental shift in our understanding of the planet. The reason for this color misconception lies in the way we process and interpret astronomical data. Colors in space images are often enhanced or altered to emphasize certain features or to make them more distinguishable to the human eye. In the case of Neptune, these enhancements over time have led to a collective opinion of its deep blue color. So, what led to this discovery? The key lies in a meticulous study entitled Modeling the Seasonal Cycle of Uranus's Color and Magnitude and Comparison with Neptune. This study, led by Patrick G.J. Irwin of Oxford University, along with a team of experts, set out to unravel the mysteries of Uranus's seasonal color changes. However, their journey will inadvertently shed light on the true colors of Neptune, disproving long-held beliefs. The team carefully analyzed a huge array of data obtained from Lowell Observatory over 6 decades. These data, supplemented by Hubble Space Telescope observations, produced a detailed picture of Uranus's disk-averaged color and photometric magnitude, revealing the complex interplay of its seasonal changes. One of the most important aspects of this study was the focus on the reflectivity of Uranus and the abundance of methane. The researchers unraveled a complex relationship between the lower methane content at polar latitudes and the different reflectivity of aerosol particles. This complex interaction of elements in the atmosphere of Uranus was thought to be influenced by the presence of methane ice particles, adding a new layer of complexity to our understanding. In parallel, the study allowed for a fascinating comparison with Neptune. Contrary to popular belief, the difference in blue hues between Neptune and Uranus was less pronounced. This discovery was the result of a critical reassessment of Neptune's color, disproving the image of deep blue that had been ingrained in our minds. The methodology used by the team was a combination of quantitative analysis, atmospheric modeling, and advanced spectroscopic observations. They converted measured reflectance spectra into radiance spectra, and then into tri-stimulus values. This process mimicked the visible colors of the planets as perceived by the human eye, bridging the gap between the raw data and our visual interpretation. The use of advanced telescopes such as Hubble and the Very Large Telescope played an important role in this endeavor. These technological marvels allowed the team to revisit and re-examine the true colors of Uranus and, by extension, Neptune, with unprecedented accuracy. As we delve deeper into the mysteries of Neptune, we find ourselves amid a maelstrom of atmospheric activity, in stark contrast to the relative calm of its stellar neighbor Uranus. Neptune's atmosphere, a turbulent and dynamic formation, is home to some of the most extreme weather in our solar system. One of the most striking features of Neptune's atmosphere is the presence of colossal storms, the most famous of which is the Big Dark Spot. Discovered by the Voyager 2 spacecraft in 1989, this massive storm, similar to Jupiter's Great Red Spot, is a testament to the turbulent nature of the planet. A large, dark spot, a giant rotating storm, is a window into Neptune's intense atmospheric dynamics. These storms are caused by the strongest winds in the solar system, reaching speeds of up to 1,300 miles per hour. However, to this day, the power and magnitude of these winds are a mystery to scientists, raising questions about their origin and the energy sources that drive them. In contrast, neighboring Uranus is a picture of tranquility. Its atmosphere, although composed of hydrogen, helium, and methane, does not have the same violent storms and extreme winds as Neptune. The difference in atmospheric activity between these two ice giants is one of the many mysteries of our solar system. Another intriguing aspect of Neptune's atmosphere is the presence of unusual hotspots, where temperatures can reach a staggering 750 degrees Kelvin. These hotspots represent a paradox because they exist on a planet so far from the Sun. The source of this heat remains a mystery, but theories suggest it could be caused by internal processes such as auroras or magnetic reconnection in the plasma layers. The origin of these hotspots and the extreme weather conditions on Neptune are the subject of ongoing research. They force us to seek new answers to questions about planetary atmospheres and hint at complex internal processes that have yet to be understood. Stepping outside Neptune's turbulent atmosphere, we enter a realm of celestial harmony where moons and rings swirl around this icy giant. Turning our gaze to Triton, Neptune's largest and most intriguing moon, we discover a world of seasonal changes and atmospheric mysteries. Triton, a unique moon with a retrograde orbit, was the last solid object visited by the Voyager 2 spacecraft during its historic journey through the outer solar system. Because of its retrograde orbit, indicating that it was captured by Neptune's gravity, Triton stands out among the moons of our solar system. Its surface, covered in nitrogen ice, is geologically young and active, with dark green streaks indicating the presence of geysers spewing nitrogen gas. Triton's thin atmosphere, whose thickness varies with the seasons, is a fascinating study in extraterrestrial meteorology. Observations with the European Southern Observatory's Very Large Telescope have revealed that Triton's southern hemisphere is in the height of summer. This distant moon, despite its relative distance from the Sun, is experiencing significant atmospheric changes. The heat of the summer sun causes the thin layer of frozen nitrogen, methane, and carbon monoxide on Triton's surface to sublimate into gas. This process causes the icy atmosphere to thicken as the season continues in Neptune's 165 Earth-year orbit around the Sun. The season on Triton lasted more than 40 years, and the southern summer solstice occurred in 2000. The discovery of carbon monoxide in Triton's atmosphere, as well as the confirmation of the presence of methane, marked a significant advance in our understanding of this moon. The presence of these gases, especially the enrichment of ice with carbon monoxide in the upper surface layer, feeds the atmosphere and determines its seasonal dynamics. These findings required a revision of Triton's climate and atmospheric models. The complex interaction of nitrogen, methane, and carbon monoxide not only determines atmospheric conditions, but also provides insight into the geologic and climatic history of the Moon. But Triton is not alone. The planet is accompanied by a retinue of smaller moons, each contributing to our understanding of this distant world. These moons also show seasonal changes and provide insight into the complex gravitational interactions and environmental conditions around Neptune. When we turn our gaze from the moons to Neptune's rings, we encounter another aspect of this planet's mysterious nature. Neptune's rings, made up of a mixture of dust and ice particles, are dull yet mesmerizing. They testify to the planet's dynamic history. Scientists believe they're remnants of moons that were destroyed by collisions or torn apart by Neptune's gravity. The composition and characteristics of these rings are closely related to Neptune's true color and atmospheric phenomena. The subtle hue of the rings, which were affected by light scattering in Neptune's atmosphere, add another layer to the planet's color palette. The rings, reflecting and refracting light from the Sun, create the overall appearance of Neptune seen from afar. In 2022, the James Webb Telescope captured the clearest view of the rings of this distant planet in 30 years. Photographed with unprecedented clarity, these rings have changed the way we think about this distant planet. The most striking thing about the new Webb image is the clear view of Neptune's rings. Some of these rings, dim and dusty, have not been detected since the historic Voyager 2 flyby in 1989. The Webb telescope, with its enhanced capabilities, has brought these elusive rings back into focus. Neptune's rings are made up of several bright and narrow, as well as fainter dust bands. Infrared imaging by the Webb telescope has put these rings in a new light, revealing features that were previously hidden in the darkness of space. This is the first time these rings have been seen in the infrared spectrum, providing new insights into their composition and behavior. Neptune's rings, like the planet itself, are characterized by a unique composition. Unlike the gas giants Jupiter and Saturn, Neptune is an ice giant, rich in elements heavier than hydrogen and helium. This composition also reflected in the planet's signature blue color in visible wavelengths caused by a small amount of methane gas. In infrared images taken by Webb's NIRCam, near-infrared camera, Neptune does not appear blue, in contrast to the darkened appearance one would expect due to methane absorption of light. In infrared images taken by the Space Telescope, Neptune appears as a luminous, glowing white sphere. This absorption also affects the appearance of Neptune's rings, as they reflect and refract light traveling through the planet's atmosphere. This unexpected brightness in the infrared is the result of a unique interaction between the planet's atmosphere and infrared light. While methane gas absorbs red and infrared light, high-altitude clouds in Neptune's atmosphere reflect sunlight before it's absorbed. These methane ice clouds appear as bright streaks and spots that cast a ghostly glow on the planet in the infrared spectrum. By the way, you may wonder why Triton looks like a dazzling point of light adorned with shining spikes, as opposed to the more subdued image of Neptune. These diffraction spike patterns are a characteristic feature of the imaging telescope. They're not physical structures, but rather optical artifacts created by the telescope's design. Light from Triton passing through the mirrors and telescope structure is diffracted, resulting in these striking peaks emitted by the Moon. Diffraction, in simple terms, is what happens when a wave, such as light, travels around the edge of an object or through a small opening. Imagine light in the form of water waves flowing through a narrow slit in a wall. When the waves pass through the slit, they diverge in different directions, instead of just going straight through. This propagation of waves after passing through a hole or around an edge is what we call diffraction. In the context of the James Webb Space Telescope and its images, diffraction peaks arise because of the way the mirrors and structure of the telescope are arranged. When light from a bright object, such as a star or Triton in images of Neptune, enters the telescope, it's bent slightly by the edges of the mirrors and other parts of the telescope. As a result of this bending, the light diverges and forms the star-like spikes we see in the images. The study of Neptune's rings, especially in the infrared, provides valuable insights into the atmospheric conditions and internal composition of the planet. The interaction of the rings with Neptune's atmosphere, particularly the methane ice clouds, provides insights into the planet's climatic and environmental processes. The bright equatorial band that girdles the planet hints at the global atmospheric circulation, a key driver of the planet's winds and storms. The atmosphere, which sinks and warms near the equator, glows more intensely in the infrared than the cooler gases that surround it. As we conclude our journey through the mysterious world of Neptune, we reflect on the impact these discoveries are having on the broader field of planetary science and exoplanet exploration. Neptune, once a distant blue spot, is now a testament to space exploration's dynamic and ever-evolving nature. Discoveries concerning Neptune's true color, its atmospheric phenomena, and the intricate details of its rings and moons go far beyond our solar system. They provide a crucial example for understanding similar ice giants and exoplanets in the far reaches of our galaxy. The insights gained from Neptune will help astronomers decipher the mysteries of these distant worlds and enrich our knowledge of the universe. As we continue to gaze into the cosmos, Neptune reminds us of the limitless potential for discovery. Its example encourages us to keep looking, asking questions, and unraveling the mysteries of the universe. Saturn has captivated the human imagination. From ancient civilizations to modern astronomers, the Maori of New Zealand, separated by vast oceans and without telescopes, somehow knew that Saturn had rings. How? The mystery deepens. Saturn has long been a symbol of the unknown and mysterious. Its iconic rings have been the subject of wonder and speculation since the time of Galileo. But what if we told you that these rings, however eternal they may seem, are actually a fleeting cosmic phenomenon? Adding to the intrigue is a storm twice the width of Earth, with a mysterious hexagonal shape that's raging at Saturn's North Pole. What forces could have created such a geometrically perfect formation? But the mysteries don't end there. Saturn's satellites, Titan and Enceladus, offer conditions that could potentially support life. Lakes of liquid methane and geysers spewing water and organic material into space make these satellites more than just celestial bodies. They're potential homes for life. Join us for a closer look at this enigmatic giant and its cosmic mysteries. Our journey begins with Galileo Galilei, the Italian astronomer who first pointed his telescope at Saturn in 1610. What he saw puzzled him, a planet with something like ears. He didn't realize he was looking at the edges of Saturn's magnificent rings, a feature that would puzzle astronomers for centuries to come. Galileo's telescope was primitive by today's standards, and the true nature of Saturn's ears remained a mystery. It was not until 1655 that Christian Huygens, armed with a more advanced telescope, correctly identified them as a system of rings surrounding the planet. Moving into the modern era, we witnessed the Pioneer 11 mission, the first spacecraft to fly past Saturn in 1979. This mission provided us with the first close-up images of the planet and its rings, revealing intricate details that were once inaccessible to Earth's telescopes and us. But it was the Cassini mission that truly revealed Saturn in all its glory. Launched in 1997 and arriving at Saturn in 2004, Cassini spent 13 years studying the planet, its rings, and its satellites. From discovering plumes of water ice on Enceladus to capturing the ethereal beauty of a hexagonal-shaped storm at Saturn's North Pole, Cassini revolutionized our understanding of this distant world. And here's an interesting point. Long before the advent of telescopes, the Maori people of New Zealand had myths that described Saturn as having a parero, or belt, around it. How they knew this remains a matter of debate and speculation. But as we'll see later, Saturn holds more than one mystery. What do you think could have created a hexagonal storm with an area larger than the Earth itself? Saturn harbors a geometric enigma at its North Pole, a six-sided storm that's puzzled scientists for decades. This six-sided wonder is not just a superficial feature, but a deep and enduring mystery that breaks down the understanding of fluid dynamics and planetary atmospheres. The hexagon was first discovered in 1981 by the Voyager spacecraft. But it wasn't until the Cassini mission, which orbited Saturn from 2004 to 2017, that we got a front-row seat to this cosmic spectacle. Cassini's high-resolution images showed a symmetrical jet stream surrounding the hurricane-like vortex at the center of the hexagon. Unlike Earth's chaotic weather systems, Saturn's hexagon is a masterpiece of geometric precision. So what's causing this hexagonal storm? Researchers at Harvard University have developed a 3D model that suggests deep thermal convection in Saturn's outer layers may be the culprit. This model shows that the storm could spread thousands of kilometers deep into Saturn's atmosphere, well beyond what we can see. Interestingly, scientists have been able to reproduce the hexagonal pattern in a laboratory setting. Although these experiments do not capture all the nuances of Saturn's complex atmosphere, they provide a glimpse of extraterrestrial phenomena. Saturn's hexagonal vortex contrasts sharply with Earth's polar vortex, which is irregular and less stable. This difference raises questions about the fundamental properties that distinguish the atmospheres of the gas giants from the Earth group planets. The longevity of the hexagon is another mystery. It's been observed for at least 4 decades, and possibly much longer. This steady feature suggests that everything that feeds the hexagon is not a temporary phenomenon, but a stable, perhaps even permanent, aspect of Saturn's internal dynamics. Let's shift our attention from the mystery of the hexagon to another wonder of Saturn. Saturn's rings are more than just celestial jewelry. They're dynamic, ever-changing systems that interest astronomers and the public alike. But what are these rings made of, and why are they so short-lived? Saturn's rings are composed mostly of water ice with a mixture of dust and rocky material. They range in size from tiny particles to huge chunks the size of houses. These ice particles are not static. They're in constant motion under the influence of Saturn's gravity and the gravitational pull of its satellites. The rings are divided into several subdivisions and gaps, each with its own unique characteristics. Most notable are the A, B, and C rings, separated by gaps, such as the Cassini ring, a gap 3,000 miles between the A and B rings. The origin of Saturn's rings has been the subject of debate. One popular theory suggests that they formed from the remnants of a shattered moon. Another theory states that they're the remnants of material from the formation of the solar system, captured by Saturn's gravitational pull. Recent research has also shown that the rings may be much younger than Saturn itself, perhaps around 400 million years old, based on the rate of dust contamination. Saturn's rings don't last forever. They're slowly disappearing because of a phenomenon known as ring rain, in which ring particles are drawn into Saturn's atmosphere. This process is accelerated by micrometeoroid bombardment and interaction with Saturn's magnetic field. At the current rate, some scientists predict that Saturn's rings could disappear within 100 million years. The depletion of the rings would not only change Saturn's appearance, but could also have consequences for its atmosphere and magnetic field. As we pause for a moment, we realize that even the most fascinating features of our universe are not immune to the inexorable forces of physics, doomed to disappear into the chronicle of eternity. Saturn, the ringed giant of our solar system, is not just a celestial wonder. It's also a cosmic playground that contains some of the most intriguing satellites, two of which, Titan and Enceladus, have fascinated scientists and sparked debate about the potential for life beyond Earth. Titan, Saturn's largest satellite, is a world shrouded in mystery. Its dense atmosphere is rich in organic compounds, and there are lakes and rivers of liquid methane on the surface. But what's truly amazing is Titan's rate of removal from Saturn, 100 times faster than previously thought, amounting to a staggering 4.3 inches per year. This rapid drift suggests a dynamic and evolving relationship between Titan and Saturn. Could this drift affect Titan's internal dynamics? And perhaps even its potential for the existence of life. An atmosphere rich in organic compounds such as nitrogen and methane, and the possibility of an underground ocean, make Titan a tempting target for the search for extraterrestrial life. But the question remains, what would life look like in an environment so radically different from Earth's? And let's remember Enceladus, another satellite of Saturn that's very different from Titan. It's an icy world, with a highly reflective surface that outshines any other body in the solar system. Enceladus takes the concept of an ocean world to a new level. Not only does it have a subsurface ocean, but it also sprays it into space, where samples of it can be collected by a space probe. This ocean contains most of the chemical ingredients necessary for life, including hot, mineral-rich water erupting from hydrothermal vents. Hydrothermal vents can provide the necessary conditions for life as we know it. On Earth, these vents are teeming with life forms that thrive in extreme conditions. Could Enceladus's vents be home to similar but alien life forms? Enceladus also contributes to Saturn's E-ring, a unique characteristic that further enriches the dynamic relationship between the Moon and its host planet. The icy particles in this ring open a window into the Moon's internal chemistry, providing clues that may reveal its secrets. Titan and Enceladus are two moons orbiting the same planet, but quite different in their characteristics. Both present compelling arguments in favor of the potential for life, fueling our curiosity. As we ponder the possibilities of life on Saturn's satellites, it's worth noting that our curiosity is not limited to telescopes and computer modeling. Upcoming missions aim to study these satellites up close and perhaps answer some of our most pressing questions. Meet Dragonfly, NASA's ambitious mission to Titan. Scheduled for launch in the 2030s, this rotorcraft will fly over Titan's diverse terrain, from dunes to impact craters. Dragonfly's main goal is to search for the building blocks of life. It will analyze complex organic compounds in the atmosphere and on the surface, providing invaluable data on Titan's chemistry. Equipped with a suite of scientific instruments, Dragonfly seeks to understand the geologic processes on the Moon and how they relate to its potential for life. Could Titan's unique chemical composition and liquid methane cycles offer a different recipe for life? Although no missions to Enceladus are currently planned, the Moon's potential for life has made it a prime candidate for future exploration. Scientists are proposing missions that could fly through Enceladus's plumes and directly sample its underground ocean. Such a mission could analyze the chemistry of the plumes in search of signs of life or prebiotic chemistry. The presence of hydrothermal vents in Enceladus's oceans adds another layer of intrigue. suggesting an environment in which life could potentially thrive. Despite the technical challenges, a mission to Enceladus could revolutionize our understanding of the potential for life in the solar system. It could provide direct evidence for the existence of extraterrestrial life, or at least provide clues to the conditions necessary for life to exist. As we mentioned, Saturn's rings don't last forever, as we once thought. Recent studies have shown that a process that can last hundreds of millions of years is causing these icy wonders to slowly fade away. But what significance does this have for Saturn and its complex atmospheric dynamics? According to a study by the Japan Aerospace Exploration Agency, this material, composed mostly of water, causes a decrease in electron density in Saturn's atmosphere. This phenomenon, known as ring rain, significantly affects Saturn's atmospheric conditions. Ring rain is not just a trickle. It's a stream that carries away water in amounts equivalent to an Olympic-sized swimming pool every half hour. Compounding the mystery is the relative youth of Saturn's rings. Although Saturn itself is about 4.6 billion years old, data from NASA's Cassini mission suggests that the rings may be only a few 100 million years old. This leads us to wonder, if Saturn's rings are so young, what catastrophic event could have led to their formation? Was it the destruction of a moon? Or perhaps the capture of a passing comet? Cassini's Space Dust Analyzer has added another layer of complexity. Over 13 years, it's collected 163 dust particles that came from outside the Saturn system. Surprisingly, the rings turned out to be quite clean, suggesting that they hadn't existed long enough to accumulate excess cosmic dust. This cleanliness raises the question, if the rings are young, why haven't they collected more cosmic dust? The absence of cosmic dust in the rings challenges our understanding of their age and their interaction with the wider cosmic environment. It's as if the rings are in a cosmic laboratory room or clean room, isolated from the dust that permeates the rest of the solar system. As the rings are depleted, Saturn's appearance will undergo a dramatic transformation. These rings have been the planet's hallmark. Their disappearance would not only change Saturn's appearance, but could also have unknown consequences for its atmosphere, perhaps even affecting the planet's albedo and heat retention. The loss of the rings could have a cascading effect on Saturn's atmosphere, potentially altering wind patterns and even affecting the planet's iconic storms. The full extent of these changes is still unknown, making them a subject of intense scientific interest. Interestingly, the fate of Saturn's rings may be inextricably linked to its satellites. Some theories suggest that gravitational instability may have destroyed some of the icy satellites orbiting Saturn, providing enough material to form the rings. Saturn's rings and satellites are like partners in a cosmic dance, each affecting the other in subtle but significant ways. As we continue to study these celestial bodies, we can say unequivocally that the fate of one can shed light on the mysteries of the other. In the vast theater of our solar system, where planets like Jupiter and Saturn often attract attention with their majestic rings and violent storms, lies a distant world shrouded in mystery and intrigue. This is Uranus, an enigmatic ice giant that often goes unnoticed, but holds secrets that may unravel some of the most enduring mysteries of the cosmos. Far beyond the asteroid belt, nestled between the orbits of Saturn and Neptune, Uranus travels through the cold and dark corners of our solar system. It's a world that lives at a different rhythm, spinning on its side, an oddity that's long puzzled astronomers and spawned countless theories. Discovered in 1781 by William Herschel, Uranus was the first planet discovered through a telescope, extending the known boundaries of our solar system. For centuries, this distant world was just a speck of light in our telescopes, a ghostly blue ball, distant and aloof, keeping its secrets. But now, with the advent of the James Webb Space Telescope, a new chapter in the exploration of Uranus is opening. JWST, with its unprecedented vision, peels back the layers of this icy giant, revealing a world of amazing beauty and complexity. Let's travel together to this mysterious ice giant and learn about the latest discoveries made by the James Webb Space Telescope. In the quest to understand the universe, humankind has launched a sentinel into space, a marvel of engineering and a testament to our insatiable curiosity. This sentinel is the James Webb Space Telescope, the most advanced and powerful space telescope ever built, the successor to the legendary Hubble Space Telescope. Equipped with a set of advanced instruments and a mirror more than 6.5 meters in diameter, JWST is designed to observe the universe in light invisible to the human eye, the infrared spectrum. This allows the telescope to peer through clouds of cosmic dust, discover distant galaxies, and study the atmospheres of exoplanets. The telescope's journey into space was a feat in itself. Launched on an Ariane 5 rocket, JWST traveled to a point in space known as the Second Lagrange Point, or L2, 1,000,000 miles from Earth. Here, in this stable orbit, JWST can observe the universe with minimal interference from Earth and the Sun. JWST's capabilities are not limited to observing the early universe or distant galaxies. It plays a key role in unlocking the mysteries of our solar system. Its powerful instruments, such as the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, reveal new details about planets, moons, and other celestial bodies closer to home. Take Uranus, for example. In the past, our view of this distant planet was limited to faint images from telescopes such as Hubble. But now, thanks to JWST's enhanced infrared capabilities, we can see Uranus in a new light. The telescope's sensitive instruments allow us to observe the planet's atmosphere, weather patterns, and even its mysterious rings with unprecedented clarity. By analyzing the light of Uranus, JWST can decipher the chemical composition of its atmosphere, revealing the presence of gases such as methane and hydrogen. This not only helps us understand the current state of Uranus, but also provides clues about its formation and evolution. The James Webb Space Telescope continues to exceed expectations, revealing more details about our universe every day. Its latest triumph is a series of images of Uranus taken very recently, surpassing even the stunning observations made in April 2023. In early 2023, JWST provided us with unprecedented views of Uranus, allowing us to look at the planet's atmospheric dynamics and ring system in a new light. The recent images, however, are a step further. Not only are they clear, they reveal aspects of Uranus that were previously hidden or obscured, even in April observations. Take the rings of Uranus, for example. The latest images show them with even greater clarity. We can now observe finer structures within the rings and even detect faint dust bands that were previously invisible, such as the Zeta ring, the incredibly thin ring closest to the planet. The strength of JWST lies not only in its one-off observations, but also in its ability to continuously track celestial objects. Continuous observations of Uranus have allowed us to observe changes in the planet's atmosphere, track the movement of its clouds, and observe the evolution of its storms over time. The changes in the polar regions are particularly striking. Bright white caps and dark bands near the poles, the origin of which is still unclear, have shown marked changes. This continuous observation provides invaluable data for understanding the seasonal changes and long-term climate patterns of Uranus. In the set of planets in our solar system, Uranus stands out with a peculiar feature, an extraordinary axial tilt. Unlike any other planet, Uranus rotates practically on its side, tilted at an angle of about 98 degrees. This unique orientation has long intrigued astronomers and sparked a quest to understand its origin and consequences. To understand the significance of this tilt, we must travel back in time to the early days of our solar system. Uranus probably formed with a much less severe tilt. The prevailing theory suggests that a catastrophic event, perhaps a collision with a planet-sized object, dramatically changed its orientation. This colossal impact would have thrown Uranus aside, changing the definition of its axis of rotation. Such a dramatic event in the planet's history probably not only changed its rotation, but also left an indelible mark on its entire system, including its satellites and rings. Today, this lateral rotation is a unique spectacle. Each pole of Uranus is alternately flooded with sunlight and plunged into darkness at intervals of 42 years. This extreme tilt results in extreme seasons, unlike those observed on other planets. The implications for planetary observations and research are enormous. Uranus's tilt allows us to observe its rings and satellites from different perspectives, offering insights into their composition and dynamics. For example, when Uranus's rings face the Earth, they become nearly invisible, exposing fainter dust bands and smaller satellites. Compare that to Earth, which is tilted only 23.5 degrees. Uranus's extreme tilt causes drastic changes in its weather patterns, which is a goldmine for scientists studying planetary climate. Tilt also affects the circulation of Uranus's atmosphere. Prolonged exposure to sunlight at the poles can result in complex weather systems, as seen in recent JWST images. These systems are very different from those on other planets and provide a unique laboratory for understanding atmospheric physics. Let's take a journey on one Uranian year. Each season on Uranus lasts about 21 Earth years, a consequence of its 84-year orbit around the Sun. This extended duration means that each hemisphere experiences long periods of daylight, followed by equally long nights. As a result, the planet undergoes dramatic changes in appearance and climate. Because one pole of Uranus basks in uninterrupted sunlight, summers are long, while the opposite pole plunges into a deep, dark winter. This stark contrast creates unique atmospheric conditions, causing complex weather patterns and climatic shifts. The impact of these seasonal changes on Uranus's atmosphere is profound. When the sun illuminates the planet's surface, it warms the atmosphere, creating colossal storms and dynamic cloud systems. These atmospheric phenomena are not static. They evolve and change with the seasons, painting an ever-changing portrait of the planet. Among the most striking features are the bright cloud tops that appear when the sun illuminates the planet's atmosphere. These clouds, composed of frozen methane and other gases, reflect sunlight, creating a dazzling spectacle. Conversely, dark storm patches that look like giant hurricanes roam the planet's surface. Moreover, the planet's seasonal phenomena affect not only the planet itself, but also its moons. One recent study of Uranus's moons, or rather a phenomenon that's particularly intriguing, is the development of temporary atmospheres on these moons, a spectacle caused by the unique conditions of the Uranus system. The key to understanding these temporary atmospheres lies in the extreme tilt of Uranus's axis and its effect on the satellite's orbits. As these satellites orbit the planet, they experience dramatic changes in solar exposure, alternating between long periods of intense sunlight and prolonged darkness. During a long summer exposed to sunlight, the icy surfaces of these satellites undergo a process known as sublimation. The ice, composed mainly of water, methane, and carbon dioxide, transforms directly from solid to a gas, bypassing the liquid phase. This sublimation creates thin, temporary atmospheres, or exospheres, that envelop the satellites. These exospheres are most pronounced when moons are warmest. Recent research by the James Webb Space Telescope shows that this phenomena is more dynamic and complex than previously thought. Exospheres are heterogeneous. They vary in composition and density, depending on the topography of the moons and the intensity of solar radiation. As the satellites enter their winter phase, the exospheres gradually dissipate. Gases recondense on the surface, returning to an icy state. This cycle of atmosphere creation and disappearance is a unique characteristic of Uranus's satellites, opening a window into the interaction between solar radiation and surface ice. The rings of Uranus, often overshadowed by the majestic rings of Saturn, hold their own tale of cosmic intrigue and dynamism. A recent comparative study of the rings of Uranus, Saturn, and Jupiter sheds new light on these lesser-known, but no less fascinating, celestial features. In contrast to the wide and bright rings of Saturn, the rings of Uranus are narrow, dim, and less extensive, extending to 4 planetary radii. This includes elusive rings, such as the Mu and Nu rings. The study delves into the gravitational influence of Uranus's main satellites on these rings, a key factor in their formation and evolution. The significant influence of Uranus's 5 major satellites, Miranda, Ariel, Umbriel, Titania, and Oberon, plays a central role in the history of the rings. These satellites, much more massive than their smaller counterparts, dominate the gravitational dynamics within the Uranus system. Their positions and masses relative to Uranus provide a better understanding of the formation of the satellites and the gravitational formation of the rings. The formation of Uranus's rings is attributed to a combination of processes, including collisions, satellite breakup, and gas release from the main satellites. These dynamical processes affect the material composition of the rings and are influenced by the ever-changing environment of the Uranus system. The stability of the rings is intrinsically linked to their dynamical interactions with the satellites of Uranus. The study examines how accretionary processes occur within the Roche limit and how the dynamics of shepherding moons play a crucial role in maintaining the rings. In addition, the rings provide a unique opportunity to understand the internal structure of Uranus through seismological studies. Modeling results show how these satellites shape the ring system, affecting its structure and stability over time. The modeling predicts significant material loss within the ring system, primarily due to gravitational interaction with the satellites. The complex dance between moons and rings is a key aspect of the Uranus system. The dynamic exclusion zones created by the satellites and the influence of these zones on the material distribution of the rings are crucial to understanding the structure and the evolution of the rings. The study also examines the role of satellite-to-satellite interactions in the evolution of the system, especially past resonances between satellites such as Ariel and Umbriel, and their impact on the orbits and geology of satellites, especially Miranda. But the mysteries surrounding this planet don't end there. You've probably heard of the aurora borealis. Well, the latest discovery concerns the auroras of Uranus, which also has them. However, its auroras, unlike Earth's, occur in the infrared spectrum. Using the Keck 2 telescope, astronomers observed enhanced emissions of trihydrogen cation in the planet's atmosphere. This is a groundbreaking discovery that sheds light on the unique magnetic field and dynamics of Uranus's atmosphere. Uranus's magnetic field, which is significantly deflected from the planet's axis of rotation, creates a unique coupling of the magnetosphere, ionosphere, and thermosphere. The detection of these infrared auroras is crucial because it opens up a new window into these processes, previously elusive due to the lack of such detections on Uranus. Comparing the polar auroras of Uranus with those of Jupiter and Saturn reveals their different characteristics. Unlike Jupiter, where the H3+ emissions have short lifetimes that smooth out the variability of the UV emission. The brightest infrared emissions of Uranus do not necessarily coincide with the brightest UV emissions of the other planets. This unique aspect of Uranus's polar lights provides valuable information for exoplanet studies, especially for the worlds of warm ice giants. The study delves deeper into the unusual heat spots on Uranus, observed near the latitudes of the UV northern lights. These spots, analyzed for temperature, column density, and total emission, suggest that the enhancement is not caused by temperature, but rather by increased ionization, probably due to polar aurora activity. Polar lights play a significant role in heating the atmosphere, and on Uranus, the increased H3+ emissions associated with these auroras suggest their involvement in atmospheric processes. By studying such unique things, we gain a deeper understanding of similar processes in different planetary environments, enriching our knowledge of how auroras shape planetary atmospheres, affecting not only thermal properties, but also the overall dynamics of the ionosphere and magnetosphere. In the quest to unravel the mysteries of our solar system, the ice giants Uranus and Neptune are distant enigmas beckoning closer exploration. Recent research, including a fresh analysis of Voyager images, has revealed that the two planets actually have similar shades of greenish-blue color, fundamentally changing our long-held beliefs. Uranus and Neptune share many common characteristics. They're roughly the same size, have the same mass, and are surrounded by deep atmospheres of comparable materials. Nevertheless, it was long thought that their appearance was quite different. This misconception has now been corrected. Both planets are shown in their true colors, largely influenced by the methane layer in their atmospheres. The need for a dedicated mission to Uranus has never been greater. Such a mission would not only deepen our understanding of the planet itself, but also provide a comparative view of Neptune and other similar icy giants. The mission's potential goals range from studying the unique magnetic field and complex ring system to investigating atmospheric dynamics and internal structure. In an important achievement for planetary exploration, the Uranus Orbiter and Probe mission has been elevated to the highest priority for NASA flagship mission within the 2023-2032 Planetary Science Decadal Survey. Future launch windows are available between 2030 and 2034. Key science goals will include a detailed analysis of the unusual tilt of Uranus's axis and its effect on the planet's climate and weather patterns. The mission can also study the intriguing phenomena of infrared auroras and their role in heating the atmosphere, providing a comparative study with other planets. Studying Uranus and Neptune will also provide valuable information about planetary evolution and dynamics. Understanding why Uranus appears slightly whiter, perhaps due to its more stagnant atmosphere, allowing methane haze to accumulate, can tell us a lot about atmospheric processes on the ice giants. As we await a future mission to Uranus, we stand on the threshold of discoveries that could redefine our understanding of the outer solar system. Exploring this distant ice giant will not only unravel its mysteries, but will also expand our knowledge of planetology as a whole, shedding light on the complex picture of our cosmic home. The moon has always been a beacon of mystery and wonder, but beyond its radiant beauty and folkloric tales, the moon holds secrets that have eluded us for centuries. Among these mysterious features is the moon's south pole, a region shrouded in perpetual shadow and intense cold, untouched and unexplored by any previous lunar mission. This is the story of Chandrian 3, India's daring journey into uncharted territory. Launched on a journey of more than 238,600 miles, Chandrian 3 embarked on a mission not just of distance, but of discovery. Its purpose? To unravel the mysteries of the moon's south pole a place where sunlight barely reaches, an area where the terrain is so treacherous that you have to wade through an endless maze of craters and rocks. Here, in this alien landscape, Chandrian 3 sought answers to questions that have puzzled scientists for decades. What lies beneath the surface of this mysterious region? Do earthquake-like tremors shake this silent world? And the most exciting question is whether water, the elixir of life, exists here in the form of ice. When Chandrian 3 ventured beyond Earth, it carried with it the aspirations of a nation and the curiosity of the world. Its primary goal was clear, yet challenging: to achieve a soft landing near the Moon's south pole, a feat that had never before been accomplished. From the busy Mission Control Center of the Indian Space Research Organization, a team of dedicated scientists and engineers piloted this ambitious mission. Their expertise helped Chandrian 3 traverse the space void, overcoming the challenges of lunar orbit insertion and descent. The south pole of the Moon is a landscape unlike any other. Here, the terrain is a patchwork of craters and mountains, many of which are shrouded in perpetual darkness. The challenge was not just to land, but to land safely in an area where the terrain is unforgiving and most slopes are quite steep. When the Vikram landing module separated from the orbiter, it began its descent. The landing module, equipped with advanced sensors and engines, began its perilous journey to the surface of the Moon. Imagine a spaceship autonomously navigating a maze of craters and boulders in search of a patch of land safe enough to land on. The landing module's onboard systems were hard at work, analyzing every inch of the terrain below. Against this treacherous landscape, the landing module also struggled with extreme temperatures. The Moon's south pole is a place of stark contrasts. The sun barely rises above the horizon, while shadows hide frigid temperatures that can drop to minus 382 degrees Fahrenheit. As the landing module made its final approach, the hearts in the Flight Control Center beat harder. Every second was decisive, every maneuver a test of human ingenuity and technological prowess. With a light thud, Vikram landed, marking an historic moment not only for India, but for lunar exploration in general. In the silence of the Moon's south pole, Chandrian 3 began its mission of exploration and discovery. So, after the historic landing of Chandrian 3, a new chapter in lunar exploration began. The mission's goal was to maximize the study of the Moon's characteristics, especially its elusive exosphere and ionosphere, and to establish the range of temperature variations just beneath its surface. The lunar exosphere, the thin layer of gases surrounding the Moon, holds the key to the satellite's past and present. Unlike Earth's robust atmosphere, the Moon's exosphere is so rarefied that it almost resembles a vacuum. The Chandrian 3 instruments, developed using the latest technology, are designed to measure the density and composition of this elusive layer. In addition to the exosphere, the mission delved deeper into the Moon's ionosphere. This layer, formed by solar energy ionizing atoms in the exosphere, plays a crucial role concerning lunar communication and navigation. The Chandrian 3 measurements were designed to provide unprecedented information on the density and behavior of the ionosphere, which is important for future lunar missions and potential human habitats. Another intriguing aspect of the mission was studying the temperature variations just beneath the lunar surface using one of 4 instruments on the landing module, CHASTE, or Chandra's Surface Thermophysical Experiment. The temperature probe, immersed in the lunar regolith, was tasked with the critical mission of mapping the thermal profile of the lunar soil. The results of Chandrian 3 revealed a sharp contrast in temperatures. On the surface, during a lunar day, temperatures rose dramatically to 140 degrees Fahrenheit. While just 8 centimeters deeper, they dropped significantly to 14 degrees Fahrenheit, demonstrating the lunar soil as a potential thermal insulator. This discovery provided new opportunities for future lunar habitats, suggesting that the lunar regolith could serve as a thermal insulator, protecting astronauts from the Moon's harsh extreme temperatures and harmful radiation. These studies were more than just scientific endeavors. They were stepping stones toward a future in which the moon could be a gateway to future space exploration. Mission results on the lunar exosphere, ionosphere, and subsurface temperature laid the foundation for understanding the moon's environment and its potential to support human life. Standing in the vast lunar landscape, Chandrian 3 was ready to detect a phenomenon that had not been observed for more than 50 years, a lunar earthquake. The mission succeeded in shedding light on one of the most intriguing and least understood aspects of the moon. The Instrument for Lunar Seismic Activity, or ILSA, a seismic instrument, was designed to detect the slightest tremors on the moon, and it did. Chandrian 3 detected what looked like a lunar earthquake, a significant discovery given that the last such observation was made during the Apollo missions in the early 1970s. Lunar quakes are fundamentally different from earthquakes. While Earth's seismic activity is largely due to the movement of tectonic plates, the Moon, which is devoid of these plates, experiences earthquakes for a variety of reasons. These tremors can last much longer than earthquakes, sometimes up to an hour, and their origin is a subject of scientific interest. The Chandrian 3 data suggests several possible causes for these earthquakes. One theory is a collision with meteoroids, which could cause shock waves that penetrate the Moon's crust. Another is Earth's gravitational pull, causing tidal forces that load the lunar crust. And finally, extreme temperature fluctuations on the Moon's surface can cause expansion and contraction, leading to earthquakes. These earthquakes are not just surface phenomena, they're windows into the Moon's interior. By analyzing the seismic waves, scientists can infer the composition and structure of our satellite's interior, which resembles a sonogram of the lunar interior. Such information is of great importance for understanding the formation and evolution of the Moon. The detection of a lunar earthquake by the Chandrian 3 spacecraft has not only provided a glimpse into the dynamic nature of our celestial neighbor, but has also opened up new insights into the geological processes that shape the Moon. To unravel the geologic mysteries of the Moon, Chandrian 3 carried out another exploration. Among the most intriguing finds was the discovery of sulfur, an element whose presence on the Moon has been shrouded in mystery. The Laser-Induced Breakdown Spectroscope, or LIBS rover, a marvel of scientific instrumentation, vaporizes tiny samples of lunar soil using high-energy laser pulses. When the plasma emits light, the spectroscope analyzes its wavelength, thereby revealing the presence of various elements, including sulfur. Sulfur on the Moon is a significant find. On Earth, sulfur is often associated with volcanic activity, raising questions about similar processes on the Moon in the past. Its presence could provide insight into the volcanic history of the Moon and the processes that shaped its surface. In addition to sulfur, another key objective of Chandrian 3 was the search for water ice, a search that's intrigued scientists for decades. Water ice on the Moon is not just a scientific curiosity, it's a potential resource for future human missions, offering water for life support and fuel production. Despite high hopes, Chandrian 3, like its predecessors, found no direct evidence of water ice on the Moon's surface. However, the lack of direct evidence is not a conclusion, but a clue leading to new hypotheses. One theory is cold trapping, in which water vapor can migrate to permanently shadowed craters at the poles, freezing into ice. The detection of sulfur adds another layer to this theory, as sulfur may be trapped with the water ice and released as a result of the breakdown of water molecules by high-energy solar radiation. The lack of direct evidence for the existence of water ice raises important questions. Is the ice deeper beneath the surface, shielded from detection by the insulating properties of the lunar soil? Or is its prevalence more heterogeneous and elusive than previously thought? During its exploration of the Moon's south pole, Chandrian 3 found more than just sulfur. The rover's LIBS instrument made the first ever in situ measurements of the elemental composition of the lunar surface in this region. In addition to sulfur, the instrument detected aluminum, calcium, iron, chromium, and titanium. each element reflecting part of the complex geologic history of the lunar surface. Further measurements added new details to this discovery, further revealing the presence of manganese, silicon, and oxygen. These elements, each with its own unique spectral signature, provided clues to the formation of the Moon and its evolutionary history. Studies of the presence of hydrogen, a key component in the search for water, also continue. The mission's discovery of these elements and the ongoing search for water ice underscore the dynamic and complex nature of the Moon's geology. Each discovery, each unanswered question, moves us further in our quest to understand our nearest celestial neighbor and prepares us for the next steps in lunar exploration. As the Chandrian 3 mission at the Moon's South Pole opened a new chapter in lunar exploration, it also paved the way for the next ambitious leap, the Lunar Polar Exploration Mission, LUPEX for short. This joint venture between the Indian Space Research Organization and Japan Aerospace Exploration Agency is scheduled to launch no earlier than 2026. LUPEX plans to send an unmanned lunar lander and rover to further explore the South Pole region of the Moon. JAXA will likely provide the H-3 launch vehicle and rover under development, and ISRO will provide the lander. This mission represents a significant step in international cooperation on lunar exploration. The mission's goals are multifaceted. It will demonstrate new surface exploration technologies critical for sustained lunar exploration in the polar regions. Precise landings will be achieved by using a feature-matching algorithm and navigation equipment derived from the JAXA Smart Lander for Investigating Moon mission. The LUPEX rover will carry several instruments from JAXA and ISRO, including a drill capable of collecting samples from a depth of 5 feet, 1.5 meters. Finding and analyzing water are key goals of the mission, and the potential discovery of water ice could be a game-changer for future lunar missions. In parallel with LUPEX, ISRO's Chandrian 4 mission, designed to return samples from the Moon, is in the planning stage. Scheduled for launch by 2028, Chandrian 4 will consist of 4 modules: a transition module, a descent module, an ascent module, and a re-entry module. The ambitious goal of the planned mission is to return soil samples from the Moon, which will provide invaluable information about the lunar environment. The mission will involve complex maneuvers, including sample collection, docking in lunar orbit, and returning samples to Earth. Chandrian 3's innovative discoveries, from the detection of sulfur and other elements to the study of lunar earthquakes, have revealed new layers of the Moon's mysterious nature. These results provide crucial insight into the Moon's geology, its internal structure, and the potential for future lunar habitats. Looking ahead, the future of lunar exploration is promising. Missions like LUPEX and Chandrian 4, building on the legacy of the previous ones, will continue to explore the mysteries of the Moon. India's role in these endeavors is not only that of a participant, but also that of a pioneer. Such events truly inspire us to look beyond the boundless mysteries of the cosmos.